Every second, the universe unravels its deepest secrets, offering us glimpses of phenomena that challenge everything we think we know about existence. From dazzling galaxies that stretch across the cosmos, each brimming with countless stars, to the baffling mysteries that even the sharpest minds struggle to comprehend, the universe remains a boundless source of fascination. It is a treasure trove of enigmas, each more captivating than the last, just waiting to be explored. Today, we embark on a journey into some of the most perplexing and awe-inspiring mysteries that the universe holds within its vast expanse. The universe is an unfathomable expanse filled with celestial bodies that astonish and confound. Among the most extraordinary of these are neutron stars, dense remnants of supernova explosions. Imagine a star that has burned through its life cycle, only to leave behind a core that holds the mass of approximately 2 sun-like stars, yet measures no more than 20 kilometers across. To put this into perspective, just a single teaspoon of neutron star material weighs as much as an elephant here on Earth. These stellar remnants possess a magnetic pull so intense that they can spin at mind-boggling speeds, sometimes completing a full rotation in mere milliseconds. Often, these stars emit beams of radiation, which sweep across space like the beam of a lighthouse, creating pulses that offer vital clues about their nature. In the same mysterious realm, there exists another strange entity, the rogue planet. Unlike typical planets that orbit stars, rogue planets drift through space alone, untethered to any solar system. In our galaxy alone, it is estimated that billions of these solitary wanderers exist, though their origins remain a subject of intense debate. Some scientists suggest that rogue planets were once part of a star system, only to be ejected due to gravitational forces. The existence of these planets challenges our understanding of how planetary systems form and evolve, revealing the unpredictable and often chaotic nature of cosmic processes. But perhaps the most enigmatic objects of all are black holes, regions of space where gravity is so intense that nothing, not even light, can escape. Black holes are invisible to the naked eye, but their presence can be detected through the behavior of nearby stars and gas clouds. One of the most astounding discoveries in modern astronomy is the existence of supermassive black holes, which reside at the centers of most galaxies, including our own Milky Way. These colossal black holes can contain the mass of millions or even billions of suns, and their gravitational pull plays a key role in shaping the evolution of their host galaxies. Another mystery that has captivated the minds of scientists for decades is dark matter. Although it is not a celestial object in itself, its influence permeates the entire universe. Comprising about 27% of the cosmos, dark matter affects the motion of galaxies and clusters of galaxies. Despite its significant presence, dark matter does not interact with light in any measurable way. It neither emits, absorbs, nor reflects light. This makes it undetectable by traditional means, and yet its presence is undeniable. The search for dark matter has become one of the most tantalizing quests in contemporary astrophysics, as scientists strive to uncover the secrets of this elusive substance. Each of these mysterious objects and phenomena offers a unique glimpse into the fabric of the universe, providing a window into its most complex and awe-inspiring aspects. Together, they fuel our insatiable curiosity and drive us to explore the infinite reaches of space, in search of answers to the questions that have intrigued humanity for millennia. Neutron stars and black holes are both the remnants of massive stars, but they differ drastically in their physical properties and the phenomena that surround them. When a massive star reaches the end of its life, it explodes in a supernova, leaving behind a dense core. If the mass of this core is between about 1.4 and 3 times that of our Sun, it forms a neutron star. Neutron stars are incredibly compact, so much so that a single cubic centimeter of neutron star material can weigh as much as an entire mountain here on Earth. These stars are composed almost entirely of neutrons, packed together in an incredibly dense state, generating powerful gravitational and electromagnetic fields. On the other hand, black holes form when a star's core collapses under the weight of its own gravity, surpassing a critical threshold. This collapse creates an object with gravity so intense that nothing, not even light, can escape its pull. The boundary surrounding a black hole, known as the event horizon, marks the point of no return, where the known laws of physics cease to apply. While black holes remain invisible, astronomers can observe their effects on surrounding matter, such as the acceleration of nearby material and the emission of high-energy X-rays. Around neutron stars, one can often detect the activity of pulsars, rotating neutron stars that emit beams of radiation from their magnetic poles. As these stars spin, the beams sweep across space, creating regular pulses of radiation, much like the beam of a cosmic lighthouse. This phenomenon allows astronomers to detect the periodic signals of pulsars, providing valuable insights into their nature. Neutron stars can also form binary systems with companion stars, creating dynamic interactions that may result in the emission of powerful jets and X-rays. In contrast, black holes are also capable of generating incredibly energetic jets, particularly in the vicinity of supermassive black holes found at the centers of galaxies. Material that gets too close to these behemoths forms an accretion disk, a rotating ring of gas and dust that spirals inward toward the event horizon. As the material accelerates, it heats up to extreme temperatures, emitting brilliant radiation across the electromagnetic spectrum. This cosmic interplay of matter and energy reveals the extreme conditions that exist near black holes and neutron stars, showcasing their status as some of the most extreme and intriguing objects in the universe. Quasars, or quasi-stellar objects, are among the most luminous and energetic entities in the universe. Discovered in the 1960s, quasars initially appeared to be stars due to their intense brightness. However, further investigation revealed that they are actually powered by supermassive black holes located at the centers of distant galaxies. Surrounded by swirling disks of gas and dust, these black holes pull in material, which accelerates and forms an accretion disk. As the material spirals in, it releases an enormous amount of energy, often outshining entire galaxies in the process. Quasars are considered some of the most powerful energy sources in the universe. Their immense gravitational forces convert the energy of infalling gas into light, emitting radiation across a wide range of the electromagnetic spectrum, from visible light to ultraviolet and radio waves. Some quasars emit more energy than all the stars in their host galaxy combined, making them visible even from billions of light years away. Beyond their brilliance, quasars serve as invaluable tools for understanding the universe. They act as cosmic beacons, allowing astronomers to measure the expansion of the universe and the distribution of matter in the vast, seemingly empty spaces between galaxies. By studying the light emitted by quasars, scientists have been able to learn about the composition and behavior of intergalactic matter, as well as the conditions that existed in the early universe. These celestial wonders, from neutron stars and black holes to quasars and dark matter, continue to ignite our imagination and drive our quest for knowledge. With each discovery, we inch closer to understanding the cosmos and our place within it, unraveling the mysteries of the universe one awe-inspiring revelation at a time. Quasars serve as a captivating reminder of the ever-shifting, dynamic nature of the cosmos. Far from being static entities, some of these fascinating astronomical phenomena display extraordinary fluctuations in brightness over incredibly brief periods. These sudden changes hint at the tumultuous, chaotic environments surrounding supermassive black holes, where colossal forces shape the universe in ways beyond our imagination. Every quasar is not just a distant light source. It's a testament to the immense gravitational power, the intricate dance of light, and the constant evolution of our cosmic surroundings. Meanwhile, exoplanets, planets that orbit stars outside our solar system, have become a central point of intrigue for astronomers and space enthusiasts alike. Their appeal is especially pronounced for those that reside within the habitable zone of their stars, a region often dubbed the Goldilocks zone. Here, conditions are ideal for liquid water to exist on the planet's surface, a critical ingredient for life as we understand it. The conditions within the Goldilocks zone are not too hot, not too cold, but just right, making these exoplanets a focal point in the search for life beyond Earth. What makes these distant planets so exciting is the range of characteristics they might exhibit. These planets orbit their stars at distances that allow temperatures to remain within a range where water can exist in liquid form, potentially fostering the conditions necessary for life. Many exoplanets in this zone also feature protective atmospheres that shield their surfaces from the harsh radiation of their stars, regulating temperatures and preserving stable environments. Some may even harbor geological features akin to Earth's, such as mountains, valleys, and signs of past or present water flow, furthering the tantalizing prospect that life might once have existed, or perhaps still thrives on these distant worlds. The search for exoplanets, especially those nestled within the habitable zone, is of paramount importance in our quest to understand life beyond our own planet. Discovering a planet in this zone opens up the possibility that it might support life, a thought that fuels the ambitions of space explorers. Astronomers frequently turn their attention to stars that resemble our Sun, as these are more likely to host planets with environments akin to Earth's. Notably, the discovery of Proxima Centauri b, located just 4 light-years from us, has sparked a surge in interest in interstellar exploration. This planet, in particular, fuels the dream of finding other Earth-like worlds and the potential for future missions aimed at uncovering evidence of extraterrestrial life. Studying exoplanets in the habitable zone does more than just fuel our hopes for finding life elsewhere. It provides critical insights into the origins of life on Earth. By examining these distant worlds, we can learn more about their atmospheric compositions, surface conditions, and the potential for life. With technological advancements accelerating our ability to detect and study these planets, the search for Earth-like worlds continues to capture the imagination of scientists and laypeople alike. The dream of discovering neighboring planets in the vastness of space remains one of humanity's most profound aspirations. Turning our gaze inward, gas giants like Jupiter and Saturn present an entirely different set of phenomena that distinguish them from the terrestrial planets such as Earth and Mars. Their immense size is one of the most striking features. Jupiter, the largest planet in our solar system, dwarfs Earth with a diameter more than 11 times greater. Saturn, though slightly smaller, is no less impressive, particularly with its stunning system of rings that make it one of the most visually mesmerizing objects in the night sky. The sheer scale of these planets not only sets them apart from their rocky counterparts, but also has a profound influence on their atmospheric and gravitational dynamics. In contrast to the rocky composition of terrestrial planets, gas giants like Jupiter and Saturn are primarily made up of hydrogen and helium. Their thick atmospheres stretch deep into their interiors, where pressure and temperature rise dramatically. As one descends into their clouds, conditions shift so radically that phenomena like metallic hydrogen emerge on Jupiter, a substance that exists only under extreme pressure. At the same time, these planets are known for their massive and long-lasting storms. Jupiter's Great Red Spot, for instance, is a hurricane larger than Earth itself and has been raging for centuries. Another fascinating feature of gas giants, particularly Saturn, is their iconic rings. While Jupiter, Uranus, and Neptune also have ring systems, Saturn's are the most expansive and visually striking. Made up of countless particles of ice and rock, Saturn's rings vary in composition and density, creating a spectacular display that changes constantly. Observing the rings reveals a dynamic environment in which the gravitational influence of Saturn's moons creates gaps, waves, and even intricate structures within the ring system. This stunning phenomenon highlights the intricate balance of forces at play between the planet, its moons, and the surrounding material, offering a glimpse into the forces that govern the behavior of celestial bodies. These captivating features of gas giants, combined with the enigmatic nature of quasars and exoplanets, underscore the extraordinary complexity and beauty of our universe. From the chaotic forces around black holes to the peaceful, water-laden worlds orbiting distant stars, the cosmos remains an endless source of wonder, exploration, and discovery. The vast expanse of moons that orbit gas giants adds yet another layer of intrigue to these colossal planets. Take Jupiter, for instance. It is home to more than 60 confirmed moons, including Ganymede, which is the largest moon in our entire solar system. In fact, Ganymede's size is so vast that it even exceeds that of Mercury, the smallest planet in our system. Meanwhile, Saturn, not to be outdone, possesses its own remarkable collection of moons. Titan, in particular, stands out among them, largely due to its dense atmosphere and the surreal presence of lakes filled with liquid methane on its surface. These moons, each with its unique characteristics, offer scientists a wide array of environments and conditions to explore. Some moons may mirror the early Earth in terms of geological activity, while others might harbor the potential for life beyond our planet. In studying these satellites, we gain not only a deeper understanding of our own solar system, but also crucial insights into planetary formation and evolution across the vast universe. The myriad moons around these gas giants serve as natural laboratories where processes that shape the planets we know can still be observed, giving us a closer look at the workings of the cosmos. Comets, often referred to as dirty snowballs, offer another fascinating window into the mysteries of the universe. These small celestial bodies are primarily made up of ice, dust, and organic compounds, which play a critical role in determining their behavior as they approach the sun. As comets travel from the cold, dark reaches of space toward the inner solar system, the sun's heat causes the volatile ice inside them to sublimate, turning directly from solid to gas. This process releases gas and dust particles, forming a glowing cloud around the nucleus known as the coma. The comet's tail is perhaps its most iconic feature, and its formation is deeply influenced by the object's composition. As the comet gets closer to the sun, solar radiation and the solar wind, the stream of charged particles ejected by the sun, push the gas and dust away, forming two distinct tails. The dust tail tends to follow the comet's orbital path, while the gas tail points directly away from the sun, creating a visually striking display. Depending on the comet's chemical makeup, different gases may be released, giving each comet a unique appearance with varying colors and characteristics. Not all comets behave the same way. Some, especially those rich in volatile compounds, exhibit vibrant, active tails, while others composed of rock and less ice produce weaker tails or even no tail at all. This variability results in the remarkable diversity we see in comets, with each encounter offering something new and awe-inspiring. As they near the sun, comets often become more unpredictable. They may fragment into smaller pieces or, in extreme cases, disintegrate completely. Each comet, regardless of its fate, is a relic from the early days of our solar system, offering a glimpse into the conditions that prevailed when the planets were first forming. Their bright displays and erratic behavior continue to captivate observers, and they remain a reminder of the dynamic processes that shaped our celestial neighborhood. Rogue planets have also recently become a major subject of fascination, upending many of our preconceived notions about planetary formation. These elusive worlds, which wander through the cosmos without being tethered to any star, challenge our traditional understanding of how planets come to be and how they evolve. For centuries, scientists believed that planets could only form within the gravitational embrace of a host star, accumulating material and sharing their system with other celestial bodies. The discovery of rogue planets, however, has revealed a much more chaotic and dynamic universe than we once imagined. One of the most compelling aspects of rogue planets is their sheer abundance. It's estimated that there could be billions of these free-roaming worlds in our galaxy alone, potentially even outnumbering the stars. This raises tantalizing questions about how many more planets might be lurking unseen within the vast fabric of space. These planets could have originally formed around stars before being ejected from their systems due to gravitational interactions with larger bodies. In many cases, planets that once existed as part of a star system may have become solitary travelers, roaming the galaxy without a home star. The existence of rogue planets not only broadens our understanding of planetary systems, but also opens up new realms of scientific inquiry. One of the most intriguing questions is whether these planets could support life, despite being far from any star. While it might seem improbable, there are potential scenarios in which rogue planets could retain heat through radioactive decay or harbor subsurface oceans. These environments could, in theory, offer a suitable habitat for microbial life, challenging our traditional notions of what makes a planet habitable. The discovery of rogue planets forces us to rethink the conditions that could foster life, extending our search for life beyond the familiar, habitable zones around stars. Ultimately, the study of rogue planets underscores the complexity and mystery of the universe. Each discovery adds another layer to our understanding of the cosmos, urging us to reconsider our place in it. As these planets drift through the immense void, we are reminded that there is still so much we have yet to explore and comprehend. Spiral galaxies, with their elegant pinwheel-like structures, are among the most visually captivating objects in the universe. These galaxies are defined by their spiral arms, which radiate outward from a central bulge. The arms are often filled with younger stars, along with clouds of gas and dust, giving them a bright, colorful appearance. At the galaxy's core lies an older collection of stars, typically with a yellowish hue, and in many cases, a supermassive black hole resides at the very center. The overall shape of a spiral galaxy is flattened, giving it a distinct disc-like appearance. In contrast, elliptical galaxies possess a much more rounded or elongated shape and are composed primarily of older stars, which gives them a more subdued, reddish appearance. Unlike spiral galaxies, elliptical galaxies lack the dense clouds of gas and dust that fuel star formation. As a result, these galaxies evolve more slowly, with star creation occurring at a much lower rate. This means that while spiral galaxies are often teeming with new stars, elliptical galaxies tend to feature a more uniform population of older stars. The differences in stellar populations between these two types of galaxies also reflect their distinct evolutionary paths. Spiral galaxies contain stars at various stages of life, from young, blue stars in the arms to older stars in the central bulge. In contrast, elliptical galaxies tend to be dominated by older stars, creating a more homogeneous stellar environment. The ongoing star formation in spiral galaxies and the slow evolution of elliptical galaxies serve as a reminder of the diverse processes that shape the universe's many galaxies. The behavior and dynamics of galaxies vary greatly depending on their structure, leading to some fascinating differences in how they evolve and interact. For instance, the rotation of spiral galaxies is easily seen in the sweeping motion of their arms, which appear to swirl outward. This rotational behavior is much more orderly compared to elliptical galaxies, where the motion of stars is more random. This randomness can result in frequent star collisions and interactions, something not typically observed in the predictable motions of spiral galaxies. By studying these differences, astronomers can piece together the complex evolution of galaxies and better understand the vast history of the universe. Take, for example, the Milky Way, our home galaxy, which is a prime example of the dynamic processes that shape galactic evolution. Its formation traces back more than 13 billion years, when a massive cloud of gas and dust began to collapse under the force of gravity, marking the birth of the first stars. Over time, these stars grouped into clusters, merging and evolving into the familiar spiral structure we see today, filled with stars, planets, and countless celestial phenomena. As the Milky Way grew, it continued to accumulate mass through a process known as hierarchical merging. This concept refers to the gradual merger of smaller galaxies and dark matter halos. This ongoing accretion likely played a crucial role in forming the galactic disk, a flat region containing the bright spiral arms that are home to many young stars. At the heart of the Milky Way, there likely resides a supermassive black hole, a common feature in large galaxies. This black hole serves as both a gravitational anchor for the galaxy and a source of fascinating astronomical phenomena. The Milky Way, however, is not an isolated island in the cosmos. It belongs to a small group of galaxies known as the Local Group, which contains over 50 galaxies, including the Andromeda Galaxy, the largest of them all. Like the Milky Way, Andromeda is a spiral galaxy. The Local Group presents a diverse range of galaxy types, from small dwarf galaxies to larger spiral structures. The gravitational interactions between these galaxies shape their movements, structures, and relationships, creating a dynamic cosmic environment that offers deep insights into the interconnected nature of the universe. Looking ahead, the fate of the Milky Way is intricately linked to that of Andromeda. In roughly 4 billion years, the two galaxies are on a collision course. This collision will likely trigger a dramatic transformation as the galaxies merge into a single, new structure. Such an event will not only reshape the arrangement of stars within both galaxies, but also trigger changes in their overall shapes and star distribution. The cosmic dance between the Milky Way and its neighbors offers a glimpse into the future, revealing how galaxies evolve through interactions and mergers over time. Yet, beyond the observable structures of galaxies, there exists a mysterious substance that plays a critical role in shaping the universe: dark matter. Comprising roughly 27% of the total mass and energy content of the universe, dark matter remains invisible and undetectable by traditional telescopes. It does not emit, absorb, or reflect light, making it completely invisible to our current methods of observation. Despite its elusiveness, the presence of dark matter can be inferred through its gravitational effects on visible matter, radiation, and the large-scale structure of the cosmos. One of the most compelling pieces of evidence for dark matter comes from the rotation of galaxies. When astronomers study spiral galaxies, they encounter a mystery. According to Newtonian physics, stars located at the outer edges of galaxies should move more slowly than those near the center, where the majority of a galaxy's mass resides. However, observations consistently show that the stars at the outskirts of galaxies move at unexpectedly high speeds, suggesting that there is more mass in these galaxies than can be accounted for by visible matter alone. This discrepancy points to the presence of dark matter, which, though invisible, contributes a significant amount of mass to galaxies, influencing their rotation and overall dynamics. In this way, the study of galaxies, whether it's their rotation, their structure, or their interactions, provides not only a window into the past and present of our cosmic neighborhood, but also a deeper understanding of the unseen forces shaping the universe. However, measurements reveal something shocking. Stars located far from the galactic core are traveling at speeds that defy expectations. These remarkable velocities suggest that there is a hidden force and unseen mass influencing their motion, an influence not accounted for by the visible matter within the galaxy. This discrepancy in stellar movement hints at the presence of a vast amount of dark matter, extending well beyond what current observational tools can detect. As we delve deeper into the cosmos, the mystery of dark matter intensifies, especially when we consider galaxy clusters. These massive structures contain hundreds, even thousands of galaxies, all bound together by the invisible force of gravity. But when we calculate the mass required to hold these clusters intact, using only the visible matter we can observe, the numbers fall drastically short. This is where gravitational lensing comes into play. When light from distant objects passes near a massive object, such as a galaxy cluster, it bends due to the immense gravitational pull. By observing this bending of light, astronomers have been able to map the distribution of mass in galaxy clusters, revealing an astonishing amount of unseen mass that can only be attributed to dark matter. Without it, these clusters would fly apart instead of remaining bound together. The influence of dark matter reaches beyond the structure of galaxy clusters. It stretches all the way to the very birth of galaxies themselves. Studies suggest that dark matter may have acted as a cosmic scaffolding, providing the gravitational foundation upon which ordinary matter could clump together to form stars and galaxies. Without this invisible framework, galaxies might not have formed at all. There simply wouldn't have been enough gravitational force to bring the matter together in the first place. This intricate relationship not only shapes the structure and movement of galaxies, but also plays a critical role in the ongoing evolution of the universe, making dark matter a cornerstone of modern astrophysics. The ongoing quest to unravel the secrets of the cosmos hinges on understanding this elusive force. And yet, even as we begin to comprehend the role of dark matter, the cosmos continues to astound us with its dynamic nature. When galaxies collide, they create an environment that is as chaotic as it is beautiful. Picture two colossal collections of stars, gas, and dust drawn together by the irresistible force of gravity. As these galaxies interact, their gravitational fields tug at one another, distorting their shapes and triggering a cascade of events. Among the swirling debris and gas, new stars are born. These collisions create dense regions where gas clouds are compressed under immense pressure. As the gas becomes more compact, it begins to cool down, and under the right conditions, these clouds collapse under their own gravity. The temperature and pressure rise to such extreme levels that nuclear fusion ignites and new stars emerge from the cosmic furnace. The process of star formation in these chaotic environments is breathtaking to behold. Astronomers often capture stunning images of these galactic collisions, revealing sweeping tails of stars and gas stretching across the universe. Bright flashes of light signal the formation of new stars as massive clouds of gas ignite in a radiant display. This phenomenon, known as starburst activity, can result in the formation of hundreds, sometimes thousands, of stars within just a few million years. Despite the apparent destruction of such cosmic collisions, the ultimate outcome is often constructive. The merging of galaxies creates new stars and enriches the galaxies over time, fostering ongoing growth and evolution. The cycle of collision, formation, and renewal illustrates the dynamic and creative forces at work in the universe, teaching us that even destruction can lead to new beginnings. One of the more intriguing classes of galaxies that emerge from these cosmic interactions are irregular galaxies. These galaxies stand apart from the more familiar spiral and elliptical galaxies, characterized by their lack of distinct shape. Instead, you might observe a chaotic scattering of stars, gas, and dust, with young, bright stars sprinkled throughout. This lack of structure is often the result of gravitational interactions with other galaxies, which distort their shape over time. Despite their lack of symmetry, irregular galaxies are not without their intrigue. They are often home to vigorous star formation, with many young, hot stars scattered across their disordered structures. This intense rate of star production suggests that these galaxies are actively creating new stars at a pace that exceeds that of their more orderly counterparts. Such star-forming activity offers valuable insights into the processes that govern stellar birth, especially in regions where the influence of neighboring galaxies is weaker. Irregular galaxies also serve as windows into the early stages of galaxy evolution. Since they lack the stable, well-formed structures of older galaxies, they are thought to represent a more primordial stage in the development of cosmic structures. Studying these galaxies gives scientists a rare glimpse into how galaxies form and evolve over billions of years. They are like unfinished works of art, showing us the complex interplay of forces that shape the universe. Each irregular galaxy tells a story about the birth and growth of galaxies, revealing the dynamic and ever-changing nature of the cosmos. Irregular galaxies, with their dynamic and often unstable structures, are more than just fascinating objects in the cosmos. They hold crucial clues to the evolution of the universe itself. These galaxies, characterized by their chaotic and disordered forms, are living snapshots of cosmic history. Their turbulent natures suggest a long history of interactions with the environments around them, shaping their evolution into more defined and structured forms over time. By studying these galaxies, we gain access to a much larger narrative of cosmic evolution and the formation of galaxies throughout the universe. Irregular galaxies are like time capsules that reveal the profound processes that have shaped not only their own existence, but also the broader architecture of the universe. Satellite galaxies, which are smaller galaxies that orbit larger host galaxies, offer a similar window into cosmic dynamics. These interactions between galaxies are a delicate and complex dance, shaped by the invisible forces of gravity and dark matter. As satellite galaxies move through the gravitational embrace of their larger host galaxies, they experience dramatic and sometimes violent encounters that leave lasting marks on both galaxies involved. One of the most striking outcomes of these interactions is gravitational stripping, a process where the immense gravity of the host galaxy tears away stars, gas, and dark matter from the satellite galaxy. Over time, this can lead to the satellite losing a significant portion of its mass, altering its structure and potentially even leading to its eventual disintegration. This phenomenon provides a fascinating glimpse into the life cycles of galaxies, showing how they evolve, degrade, and sometimes disappear altogether. However, not all interactions between satellite and host galaxies result in loss. Some can trigger bursts of star formation. When a satellite galaxy passes too closely to its host, the intense gravitational forces can compress gas within the satellite. This compression can spark the formation of new stars, leading to dramatic bursts of star creation in relatively short periods of time. These interactions can refresh the galactic ecosystem, triggering the birth of new stellar generations and dramatically altering the cosmic landscape. Additionally, the exchange of materials between galaxies is not uncommon during such interactions. This exchange enriches each galaxy's gas reservoir, recycling cosmic material and creating the conditions for the next wave of star formation. This cosmic recycling process further emphasizes the interconnected nature of galaxies, highlighting how each galaxy plays a role in the larger evolutionary story of the universe. The concept of the multiverse takes this interconnectedness to an even grander scale, proposing the existence of multiple, perhaps infinite, universes that exist beyond our own. Imagine, if you will, our universe as just one bubble in a vast cosmic foam. Each bubble represents a distinct universe, potentially with different physical laws and properties unfolding within them. This mind-bending idea challenges our traditional understanding of existence and has captivated the imaginations of scientists and philosophers alike. Evidence supporting the multiverse theory comes from the realms of quantum mechanics and cosmic inflation, two areas of study that have fundamentally reshaped our understanding of the universe. Quantum mechanics suggests that particles can exist in multiple states at once, leading to the intriguing idea that every possible outcome of a quantum event could create a new universe. Meanwhile, cosmic inflation, the theory that explains the rapid expansion of the universe just after the Big Bang, lends further credence to the multiverse. According to this theory, different regions of space could have inflated at different rates, creating a patchwork of universes with different properties. Some of these universes could be conducive to life, while others could be barren and inhospitable. This scenario supports the idea that our universe is just one instance in a vast, diverse, and potentially infinite multiverse. Although direct evidence for the multiverse remains elusive, the theory continues to captivate theoretical researchers. It pushes the boundaries of our understanding of fundamental physics, offering new ways to think about the nature of existence. The implications of the multiverse theory ripple through cosmology, encouraging scientists to explore how our universe fits into a larger, more complex cosmic framework. Ultimately, the theory raises profound questions about the nature of reality and our place within it. Could there be other realities as wondrous as our own, just beyond the horizon of our comprehension? String theory offers a similarly ambitious attempt to unify the fundamental forces of nature, providing a potential explanation for how gravity, electromagnetism, and nuclear forces all operate within the universe. At its core, string theory posits that the building blocks of the universe are not point-like particles, as traditionally thought, but rather tiny vibrating strings. The way these strings vibrate determines the type of particle they represent, much like the different notes that can be produced by a vibrating guitar string. This revolutionary approach suggests that all particles and forces in the universe emerge from one fundamental entity, the string. One of the most compelling aspects of string theory is its potential to reconcile two seemingly incompatible areas of physics: general relativity, which explains the force of gravity, and quantum mechanics, which governs the behavior of subatomic particles. By uniting these two frameworks, string theory could offer a more complete and unified description of the universe. This unification may offer profound insights into everything from the largest galaxies to the tiniest particles that make up the fabric of reality itself. However, string theory faces significant challenges. One of the primary hurdles is that the theory operates on a scale so small that it is beyond the reach of current experimental capabilities. The strings themselves are theorized to be incredibly minuscule, on the order of 1/10,000,000,000th of a trillionth of a meter. This makes direct observation or experimentation with strings impossible with today's technology. Without empirical evidence to back up its claims, string theory remains a highly speculative framework, one that raises questions about its testability and scientific validity. For a theory to be truly scientific, it must not only be mathematically consistent, but also capable of making testable predictions, something that string theory, at least for now, does not. Despite these challenges, string theory remains a highly influential and promising area of research in theoretical physics. It opens up new avenues for exploring the fundamental nature of the universe and offers tantalizing glimpses of a unified theory that could one day explain the deepest mysteries of reality. As scientists continue to delve into the intricacies of string theory, it may one day provide the answers to some of the most profound questions about the nature of existence itself. String theory at its core represents a mind-bending approach to understanding the universe, one that transcends traditional physics and invites us to explore realms beyond the visible. Yet, this vast landscape of potential solutions is not without its challenges. Known as the landscape problem, the sheer number of possible outcomes that string theory presents makes it incredibly difficult to pinpoint which specific version of the theory best describes our universe. With over 10 to the power of 500 potential solutions, physicists are left grappling with a seemingly infinite array of possibilities, each suggesting different versions of reality. Despite these overwhelming uncertainties, the allure of string theory remains strong. It holds the tantalizing promise that one day it could unite all known forces and particles into a single, elegant framework. Until that day comes, string theory stands as a testament to human curiosity, a shining example of our ceaseless quest to understand the cosmos. For every obstacle, for every unknown, there lies an unwavering belief that the answers to the deepest questions about our existence may one day emerge from these theoretical strings vibrating in the void of space. Meanwhile, on a vastly different scale, gravitational waves offer an equally captivating insight into the universe's most violent and energetic events. These ripples in the fabric of space-time, triggered by cataclysmic cosmic occurrences like the collision of black holes or the merging of neutron stars, are the universe's way of sending us a message. Imagine tossing a stone into a calm pond. The resulting waves ripple outward across the surface. In much the same way, when massive objects accelerate or collide, they send out gravitational waves that travel at the speed of light. These waves, like whispers of cosmic chaos, carry information about the violent forces shaping our universe. Although Albert Einstein first predicted gravitational waves over a century ago as part of his groundbreaking theory of general relativity, it took decades of painstaking work to finally confirm their existence. In 2015, the LIGO Observatory achieved this monumental feat, detecting gravitational waves for the first time and confirming a key prediction of Einstein's theory. This momentous event not only validated a cornerstone of modern physics, but also ushered in a new era of astrophysics, one in which gravitational wave astronomy opened up entirely new avenues for exploration. What sets gravitational waves apart from traditional observations made through telescopes is that they provide a distinct and vital perspective on the universe. While telescopes capture light emitted from stars, gravitational waves offer a glimpse into the hidden movements and forces that are invisible to conventional instruments. For example, when two black holes orbit each other and eventually merge, the gravitational waves generated by this event are strong enough to be detected on Earth, even if the collision occurs billions of light years away. This opens up a treasure trove of information about phenomena that are otherwise undetectable, right? Shedding light on the formation of black holes, the evolution of stars, and even the early moments of the universe itself. As technology advances, the ability to detect and study these faint ripples will only improve, offering scientists increasingly refined data. With every breakthrough, we move a little closer to solving some of astronomy's most enigmatic questions, inching toward a more profound understanding of the cosmos. Equally captivating is the concept of time dilation, a result of Einstein's theory of general relativity, which challenges our most fundamental assumptions about time itself. Time, it turns out, is not a constant, unchanging force. Instead, it behaves in strange and surprising ways, especially in the presence of massive objects like black holes. The stronger the gravitational field, the slower time passes. This warping of space-time creates an environment where time itself is stretched and compressed, influenced by the immense mass of objects like black holes. To illustrate this, imagine a clock positioned near the event horizon of a black hole, where gravity is incomprehensibly strong. To an observer far away in space, the clock would appear to tick at an agonizingly slow pace. As one moves closer to the black hole, time slows even more dramatically. This effect becomes most pronounced as one approaches the event horizon, the point beyond which nothing, not even light, can escape. For someone near the black hole, seconds might feel like days, while their distant counterpart would witness a vastly different passage of time. This phenomenon forces us to rethink our conventional understanding of time and space. In the traditional view, time was a uniform and unchanging measure. But Einstein's theory revealed that time is more like a fabric, one that stretches and bends under the influence of gravity. This discovery not only reshapes our understanding of black holes, but also deepens our insight into the fundamental structure of the universe itself. In the extreme environments around black holes, time and gravity dance together in a way that challenges our very perception of reality. Finally, the concept of cosmic inflation provides a fascinating key to understanding the early universe. It addresses one of the most perplexing questions in cosmology. Why is the universe so uniform, despite being so vast? The theory of cosmic inflation suggests that shortly after the Big Bang, the universe underwent an incredibly rapid expansion, growing exponentially in a fraction of a second. This rapid stretching, far faster than the speed of light, helped to smooth out the universe's early structure, erasing any irregularities that might have existed. Before this period of inflation, the universe was in an intensely hot and dense state. However, during inflation, regions that were once in close proximity were stretched vast distances apart, explaining why, even today, distant regions of space share the same temperature and density. This rapid expansion essentially erased the universe's initial imbalances, creating the nearly uniform cosmic backdrop we observe on a large scale. Cosmic inflation, much like time dilation and gravitational waves, invites us to look at the universe in new and unconventional ways. It challenges our understanding of space and time, revealing the underlying forces that have shaped the cosmos since its inception. As we continue to explore these concepts, we edge closer to understanding the very origins of the universe and the forces that continue to drive its evolution. Cosmic inflation is a concept that holds the key to many of the mysteries surrounding the early universe. It explains the subtle, yet crucial fluctuations observed in the cosmic microwave background radiation, an echo of the universe's infancy. These small variations, though seemingly insignificant at first glance, were the seeds from which the vast and complex structures we see today began to form. In the grand scheme of things, the universe may appear nearly uniform, but these tiny irregularities were necessary for the clumping of matter. It was this clumping that eventually led to the creation of galaxies, stars, and all the intricate patterns that populate the cosmos. Without these fluctuations, the universe would likely have remained a uniform, lifeless expanse, devoid of the rich structures we observe today. Cosmic inflation, then, does more than just provide an explanation for the early conditions of the universe. It offers a framework that elegantly connects various observed phenomena in cosmology. It ties together a seemingly chaotic beginning with the stable, vast universe we now explore and marvel at. As researchers continue to delve into the mysteries of the universe's inception, this theory has proven to be an invaluable tool. It reveals how the universe could have evolved from a violent, energetic start into the magnificent, orderly cosmos we see today. This ongoing exploration continues to inspire scientists as they seek answers to some of the most profound questions about our existence and the origins of everything around us. Dark energy, on the other hand, represents one of the most perplexing and elusive concepts in modern cosmology. It is believed to account for around 70% of the universe's total energy content, yet remains largely mysterious. The discovery of dark energy arose from observations in the late 1990s when astronomers noticed something peculiar. Not only was the universe expanding, but that expansion was accelerating at an ever-increasing rate. This unexpected behavior suggested that some kind of force, later dubbed dark energy, was responsible for pushing galaxies apart. What makes dark energy so intriguing is its apparent negative pressure. Unlike ordinary matter and energy, which are drawn together by gravity, dark energy seems to exert a repulsive force, driving galaxies away from one another. Over time, this push could have profound implications for the ultimate fate of the universe. If dark energy continues to dominate, we may be heading toward a future where galaxies are no longer bound to each other. Instead, they will drift apart, leaving behind a vast, empty void in the cosmos. This scenario, often referred to as the Big Freeze, paints a chilling picture of the universe's future. As the cosmos continues to expand, it will cool significantly. Stars will burn out, galaxies will fade, and the universe could eventually become a dark, cold, and desolate place. This theory challenges our conventional understanding of the universe and raises profound questions about its nature and its potential end. However, despite its dominance in the universe, the precise nature of dark energy remains a mystery. Scientists have proposed several theories to explain its existence, ranging from the possibility that it represents a constant energy density that fills all of space to dynamic forms of dark energy that might change over time. To truly understand the fate of the universe, it is crucial to unlock the secrets of dark energy. As research into this enigmatic force continues, our understanding of its role could dramatically alter our view of the cosmos and our place within it. Quantum entanglement, another concept that challenges our understanding of the universe, deals with the strange phenomenon where particles become linked in such a way that the state of one instantly influences the state of another, regardless of the distance between them. This means that when one particle is measured, the state of the other particle is immediately known, even if it is light years away. This phenomenon appears to defy the laws of space and time as we know them. In our everyday experience, we understand that information transfer requires a medium and that nothing can travel faster than the speed of light. Yet, entangled particles seem to operate outside these established limits, with their interaction occurring instantaneously, no matter how far apart they are. This baffling phenomenon was famously described by physicist Albert Einstein as spooky action at a distance, a term that aptly captures the mystery and strangeness of this quantum behavior. The implications of quantum entanglement are profound. It suggests that communication between entangled particles happens instantaneously, challenging our basic understanding of causality and the speed limits imposed by space and time. It raises important questions about the nature of reality itself, as well as the fundamental fabric of the universe. As scientists continue to study this phenomenon, it is likely that entanglement will play a key role in unlocking deeper insights into the strange and wonderful world of quantum mechanics, perhaps even offering new ways to understand the universe at the most fundamental level. Furthermore, the mysterious phenomenon of quantum entanglement compels us to rethink the very foundations of reality itself. If we can learn to control and utilize entanglement, it could open the door to technological advancements that were once confined to the realm of science fiction. Technologies such as quantum computing and quantum cryptography rely on these instantaneous connections between particles. These advancements promise to revolutionize the way we communicate, offering systems that are not only far faster than current methods, but also remarkably more secure. The very essence of communication could undergo a profound transformation, allowing for encryption techniques that are virtually unbreakable by classical means. By embracing the concept of quantum entanglement, we are encouraged to rethink how we view the universe itself. It challenges our traditional linear understanding of reality and pushes us to consider the possibility that the connections between particles might stretch beyond the boundaries of space and time. These quantum links, which seem to defy the classical laws of physics, suggest that the universe operates in ways far more intricate and mysterious than we have yet imagined. As we delve deeper into the science of entanglement, we find ourselves questioning everything we thought we knew about the fundamental nature of communication and connectivity. This astonishing interplay of particles offers a glimpse into a universe much more complex than we have come to understand. It reflects the ongoing journey of scientific inquiry, where each discovery leads to new questions, each one opening up fresh paths of exploration. What we are witnessing is the ongoing redefinition of how we view our reality, where science fiction becomes science fact, and the very fabric of space and time may not be as solid as we once believed. In the early 20th century, Edwin Hubble's discovery forever transformed our perception of the universe. Before his groundbreaking work, the prevailing view held that the cosmos was static, unchanging, and infinite. But through his meticulous observations of distant galaxies, Hubble uncovered a stunning reality. The universe is expanding. By studying the light emitted from these galaxies, he discovered that their light shifted toward the red end of the spectrum, a phenomenon known as redshift. This redshift indicated that these galaxies were moving away from Earth, an observation that led Hubble to propose a revolutionary idea. The farther a galaxy is from us, the faster it is receding. This discovery was monumental because it shifted the cosmic paradigm. The universe was no longer seen as a fixed and unchanging entity. It was dynamic, alive, and evolving on a grand cosmic scale. The notion that galaxies are not stationary but are instead on an ever-expanding journey away from one another gave rise to the first solid supporting what would later be known as the Big Bang Theory. This theory posits that the universe began from an incredibly hot and dense point, what we now call a singularity, and has been expanding ever since. Hubble's findings were not just important scientifically, they had profound philosophical implications as well. His work encouraged scientists, thinkers, and the public alike to reconsider the very nature of the universe and our place within it. No longer could we view ourselves as occupying a solitary, isolated space. Instead, we were part of a vast, ever-changing cosmic tapestry, a universe filled with galaxies, celestial structures, and dark expanses. The focus of cosmology shifted from a static view of the universe to one that embraced history, change, and the continuous unfolding of the cosmos itself. In recognition of his monumental contributions, the Hubble Space Telescope was named in his honor. Launched in 1990, the Hubble Space Telescope allowed astronomers to peer deeper into the universe than ever before, uncovering the mysteries of distant galaxies and stars. The telescope continues to provide groundbreaking insights, advancing our understanding of the cosmos in ways that Hubble could only have dreamed of. Today, as we gaze into the heavens, we stand on the shoulders of Edwin Hubble, ever intrigued by the mysteries that await discovery in the farthest reaches of space. In 1999, the launch of the Chandra X-ray Observatory marked a significant leap forward in our exploration of the universe. Unlike optical telescopes that observe visible light, Chandra is specifically designed to study X-rays, a form of radiation invisible to the human eye, but incredibly rich in information about high-energy cosmic phenomena. By observing the most energetic objects and events in the universe, such as black holes, supernova remnants, and neutron stars, Chandra has illuminated aspects of the universe that ordinary light simply cannot reveal. One of Chandra's most profound contributions has been its role in revealing the hidden dynamics of black holes. Through its detailed observations, we have learned how these enigmatic objects consume surrounding matter, emitting powerful jets and X-ray winds. These extreme processes provide vital clues about the environments around black holes and their significant impact on galaxy formation and evolution. Beyond black holes, Chandra's observations have also contributed immensely to our understanding of dark matter and dark energy, two of the most mysterious and elusive components of the universe. By studying the X-ray emissions from galaxy clusters, Chandra has helped scientists map the distribution of dark matter, providing crucial insights into its role in the formation of cosmic structures. These findings are critical for understanding how galaxies and clusters of galaxies interact on vast cosmic scales, offering us a deeper, more complete picture of the universe's hidden forces. In this ongoing journey of discovery, the Chandra X-ray Observatory continues to push the boundaries of our knowledge, revealing a universe that is far more complex and interconnected than we ever imagined. Each new revelation takes us a step closer to unraveling the mysteries of the cosmos, reminding us that the universe is a place of endless wonder where there is always more to learn, discover, and explore. The observatory has been instrumental in advancing our understanding of the remnants left behind by supernova explosions, which play a crucial role in distributing elements across the universe. These remnants are the cosmic byproducts of dying stars, scattering heavy elements that are essential for the formation of planets, stars, and even life itself. Through its detailed observations, the Chandra X-ray Observatory has provided invaluable insights into these remnants, offering a deeper understanding of the life cycles of stars. It has revealed the intricate processes that lead to the creation of heavy elements, which are the building blocks for everything in the universe, from the formation of planets to the very molecules that make up life. With its innovative approach, Chandra has been at the forefront of our growing comprehension of some of the most energetic phenomena in the universe, including black holes, supernova remnants, and the energetic winds emitted by dying stars. Its high-resolution X-ray imaging has allowed astronomers to peer into the most extreme environments in space, enhancing our understanding of how stars evolve, how galaxies interact, and how the universe as a whole functions at a fundamental level. The Apollo missions were another milestone in humanity's exploration of space, a remarkable series of expeditions that not only expanded our knowledge of the moon, but also set the stage for future endeavors in space exploration. One of the greatest breakthroughs from these missions came through the collection of lunar samples, nearly 400 kilograms of rock and soil brought back by astronauts. These samples have been crucial in unlocking the moon's geological history and have significantly altered our understanding of its origins. By analyzing these samples, scientists have concluded that the moon was likely formed from debris left over after a colossal collision between Earth and a Mars-sized body billions of years ago. Apollo's contributions went far beyond simply bringing back samples. The detailed examinations of these lunar rocks, coupled with the high-resolution photographs taken during the landings, provided a wealth of information about the moon's surface. This data revealed the structure, age, and composition of different regions of the moon, supporting theories about the processes that govern planetary formation. These findings have since been used to inform our understanding of similar processes on Earth and other celestial bodies, opening up new pathways for studying volcanic activity, impact cratering, and the broader mechanisms of planetary evolution. Furthermore, the Apollo missions also deepened our knowledge of the moon's internal structure. Experiments carried out on the lunar surface, such as the deployment of seismometers, allowed scientists to detect moonquakes and learn more about the composition of the moon's interior. These discoveries revealed that, much like Earth, the moon possesses a layered interior structure, with a crust, mantle, and possibly a small core. This revelation sparked further discussions about the geophysical processes that have shaped not just the moon, but other bodies in our solar system as well. The Apollo missions also played a key role in expanding the scope of human space exploration. The cutting-edge technologies developed for these missions, including advancements in spacecraft design, life support systems, and navigation, laid the groundwork for future space endeavors. The knowledge and experience gained from Apollo not only helped propel humanity's aspirations to explore Mars and other distant destinations, but also ignited a lasting passion for exploration that continues to inspire current and future generations. The legacy of Apollo extends far beyond the moon, having fundamentally altered how we view our place in the cosmos and pushing the boundaries of what is possible in space exploration. Then came the launch of the Hubble Space Telescope in 1990, a game-changing moment in our exploration of the universe. Before Hubble, astronomers were heavily reliant on ground-based telescopes, which were often hindered by Earth's atmosphere. The atmosphere created distortion and blurred images, limiting the quality and accuracy of observations. By contrast, Hubble orbits far above the atmosphere in the vacuum of space, where it can capture sharp, detailed images of distant galaxies, stars, and other celestial phenomena. Its unprecedented clarity has revolutionized our ability to study the cosmos. One of Hubble's most profound contributions has been its ability to reveal the vast diversity of galaxies in the universe. From spiral to elliptical and irregular shapes, Hubble's images have shown that galaxies come in an astonishing array of forms, challenging previous assumptions about how these cosmic structures evolve. It has presented a universe far more complex and dynamic than anyone could have imagined, a sprawling metropolis of stars and galaxies, each with its own unique story. Hubble's contributions extend beyond just the study of galaxies. The telescope has played a crucial role in our understanding of some of the most mysterious and enigmatic phenomena in the universe, including black holes and nebulae. One of its most significant discoveries was related to the rate of expansion of the universe. Through its precise measurements, Hubble confirmed that the universe is not just expanding, but that the expansion is accelerating. This startling discovery led scientists to postulate the existence of dark energy, a mysterious force driving the acceleration of the universe's expansion. This revelation has reshaped our entire understanding of cosmic dynamics, forcing us to reconsider the very nature of the universe and the forces that govern it. These advancements, from the study of supernova remnants to the revelations of Hubble, have fundamentally transformed our understanding of the universe and our place within it. They have opened new frontiers in space exploration and deepened our understanding of the fundamental processes that drive the cosmos. The work of observatories, missions like Apollo, and instruments like the Hubble Space Telescope continues to inspire awe and curiosity, urging humanity to push the boundaries of exploration even further into the unknown. Furthermore, the Hubble Space Telescope has provided us with images of far-off galaxies, their light having journeyed across billions of years to reach our eyes. This incredible technology allows astronomers to peer back in time, offering a glimpse of the universe in different stages of its evolution. Such observations grant us a perspective that was once unimaginable, helping us understand the cosmos in all its intricate complexity. The profound scale of the universe revealed by Hubble has sparked not just awe, but a deeper curiosity about our place within it. The Hubble Space Telescope's influence extends far beyond the realm of scientific observation. It has ignited the imaginations of generations, inspiring countless individuals to look up at the stars and ponder the mysteries lying beyond our home planet. Through Hubble, we no longer view the universe as a distant, inaccessible expanse, but as a dynamic and evolving entity in which we are a small yet significant part. The telescope has transformed the way we see the cosmos, shifting our understanding of both the universe and ourselves. Similarly, the Voyager missions, launched in the late 1970s, forever altered our perception of the solar system. Voyager 1 and Voyager 2 were the first spacecraft to venture beyond the familiar planetary boundaries, reaching the farthest reaches of our cosmic neighborhood. One of their most remarkable achievements was the detailed data they gathered about Jupiter and Saturn, revealing a wealth of information about these massive planets' atmospheres, their spectacular ring systems, and the numerous moons that orbit them. Among these moons, Jupiter's Europa stands out. With its surface covered in ice and signs of a subsurface ocean, Europa has since been identified as one of the most promising candidates for extraterrestrial life. Voyager 2, not content with just exploring the gas giants, also made history by journeying to the ice giants, Uranus and Neptune. It uncovered a wealth of new information about these distant planets, including Uranus's unusual axial tilt. Unlike any other planet in the solar system, Uranus rotates on its side, causing extreme seasonal variations over its long orbit. Neptune, too, surprised scientists with its vibrant and dynamic atmosphere, which hosts some of the fastest winds recorded in the solar system. These groundbreaking discoveries have reshaped our understanding of these gaseous giants, shedding light on their formation and atmospheric dynamics in ways previously thought impossible. The Voyager spacecraft didn't just explore planets, they also expanded our understanding of the heliosphere, the vast bubble-like region of space influenced by the sun's solar wind. Voyager 1's journey beyond the outer edges of our solar system marked the spacecraft's entry into interstellar space, where it began to measure cosmic rays and explore the interstellar medium. This invaluable data revealed the ways in which solar system interacts with the space around it, helping scientists clarify the boundaries of our cosmic home. The findings from Voyager 1 also suggest that the physical phenomena observed in our solar system are likely present in other star systems, providing crucial insights into interstellar environments. The Voyager missions also captured the imagination of the public with their iconic pale blue dot photograph, an image of Earth taken from millions of miles away, showing our planet as a tiny, fragile speck in the vastness of space. This humbling view has spurred reflection about the delicate nature of our existence and our responsibility to protect our home. As we look to the future, the Voyager missions remain an enduring source of inspiration. Their legacy continues to propel humanity toward exploring the farthest reaches of space, pushing the boundaries of our knowledge and understanding. The discovery of the cosmic microwave background, CMB radiation, in the 1960s marked a pivotal moment in our quest to understand the origins of the universe. This faint glow, which permeates the entire cosmos, is a remnant from the earliest moments of the universe, a time when it was still hot and dense. The discovery was made by Arno Penzias and Robert Wilson, who, while studying radio waves from the Milky Way, stumbled upon this enigmatic signal. What they found was not mere background noise, but a deep and ancient echo of the universe's birth. According to the Big Bang Theory, the universe began as an incredibly hot, dense point, approximately 13.8 billion years ago before beginning its expansion. As the universe expanded, it cooled, allowing particles to combine and form atoms. Around 380,000 years after the Big Bang, these atoms were able to interact with light that had previously been trapped by free electrons. This moment, known as recombination, allowed light to freely for the first time, creating a snapshot of the universe in its infancy. The CMB is essentially that ancient light, now stretched to microwave wavelengths due to the expansion of the universe. Its near uniformity across all observations indicates it originated from a hot, dense state. Variations in its temperature offer essential insights into the early conditions of the universe and the processes that led to the formation of galaxies and large-scale structures. The tiny fluctuations observed in this radiation are thought to be the very seeds from which all matter in the universe eventually grew. Scientists view the cosmic microwave background as one of the strongest pieces of evidence supporting the Big Bang model. Its discovery confirmed that the universe had a definite beginning and that it has been evolving ever since. With each new advancement in technology, we continue to explore the CMB in greater detail, seeking to unlock more secrets about the universe's origins and future. The discovery of pulsars, made possible by advances in radio astronomy, marked another groundbreaking milestone in astrophysics. In the late 1960s, a graduate student named Jocelyn Bell Burnell and her advisor, Anthony Hewish, were using a radio telescope in England to study quasars when they detected a series of unusually regular pulses of radio waves from a specific region of the sky. Initially, these signals were so consistent that they jokingly referred to them as coming from little green men, suspecting they might be signals from extraterrestrial civilizations. However, further investigation revealed that these signals originated from a previously unknown type of astronomical object, a pulsar. Pulsars are rapidly rotating neutron stars that emit beams of radiation from their magnetic poles. Because these beams are highly directional, they can only be detected when they sweep past Earth, much like the beam of a lighthouse. The regular pulsations occur because the neutron star rotates at astonishing speeds. Some complete a full rotation multiple times per second, leading to a predictable and stable output of radio waves. The discovery of pulsars was a monumental breakthrough, as it provided strong evidence for the existence of neutron stars, a crucial piece of the puzzle in understanding stellar evolution. The implications of pulsars extended far beyond the discovery of a new class of objects. Their incredible stability has made them invaluable tools in astrophysics. Scientists now use pulsars as cosmic clocks, allowing them to test theories of gravity and the structure of space-time with unparalleled precision. The rhythmic and predictable nature of pulsar emissions has opened new doors for understanding the fundamental forces shaping the universe. Studying pulsars within binary systems, where they orbit another star, has unlocked new paths in our exploration of gravitational waves, those ripples in the fabric of space-time that are created by massive objects accelerating through space. These waves, once purely theoretical, have now been detected, providing us with a new way to observe the universe. Radio astronomy has played a pivotal role in identifying these pulsars, and through this discovery, we've been able to enhance our understanding of the universe itself. The ability to detect and study these pulses has unveiled the extraordinary life cycles of stars, shedding light on the dynamic processes that govern their existence. As we delve further into pulsar research, we not only refine our grasp on the fundamental laws of physics, but also gain insight into the vast, ever-changing cosmos that surrounds us. This continues to be a journey of discovery, helping us understand the complexities of both the tiny and the immense aspects of our universe. At the heart of the cosmos, black holes are some of the most compelling and mysterious objects. These regions of space exhibit gravitational forces so intense that not even light can escape. This phenomenon occurs when a massive star exhausts its nuclear fuel and collapses under its own immense weight. While stellar black holes form from the collapse of a single star, there are also supermassive black holes, far larger and found at the centers of most galaxies, including our very own Milky Way. These supermassive black holes can contain millions, and in some cases even billions of times the mass of our Sun. Despite their overwhelming size and mass, these cosmic giants remain shrouded in mystery. One of their most defining features is their event horizon, the boundary beyond which not even light can return. Inside this point, the gravitational pull is so strong that the laws of physics, as we understand them, begin to break down. Black holes don't just trap matter, they dramatically influence their surroundings, often shaping the galaxies they reside in. A fascinating aspect of supermassive black holes is how they grow. They can accumulate mass by consuming gas, dust, and even stars that venture too close. This feeding process can lead to the formation of an accretion disk, a rotating disk of material that spirals toward the black hole. As this material heats up due to friction, it emits an immense amount of energy, making it one of the brightest objects in the universe, often visible across great cosmic distances. These quasars reveal not only the presence of black holes, but also provide clues about their growth and the evolution of the galaxies they inhabit. The relationship between supermassive black holes and their galaxies is intricate and fascinating. Research suggests that the mass of a black hole correlates with the mass of its host galaxy's bulge, indicating a deep connection between their development. This mutual influence raises intriguing questions about the life cycles of galaxies and pushes scientists to explore the complexities of these cosmic behemoths. As we continue to study black holes, we gain deeper insights into the workings of gravity, space, and the universe itself. Among the most powerful explosions in the universe are gamma-ray bursts, which release more energy in just a few seconds than our Sun will emit over its entire lifespan. These colossal events challenge our understanding of stellar processes in profound and unexpected ways. Traditionally, we have viewed stars as relatively stable objects, progressing through predictable life stages from birth to death, eventually ending as white dwarfs, neutron stars, or black holes. However, gamma-ray bursts occur under conditions that are only now beginning to be fully understood. Most gamma-ray bursts are thought to originate from massive stars that have depleted their nuclear fuel, leading to a catastrophic collapse. This collapse forms a black hole or neutron star and is accompanied by jets of highly energetic particles that travel at nearly the speed of light. These jets break through the star's outer layers, releasing a brilliant burst of gamma radiation. This discovery has fundamentally altered our understanding of stellar life cycles, revealing that they can be far more complex and violent than previously imagined. Moreover, the study of gamma-ray bursts provides valuable insights into the early universe. Because these bursts are often detected at immense distances, they offer a window into a time when the universe was much younger. Their frequency and behavior are key to understanding the history of star formation and evolution, offering clues about how stars were born and died in the cosmos's early years. These cosmic explosions not only expand our knowledge of stellar life cycles, but also serve as beacons that guide us toward deeper questions about the universe. In addition to reshaping our understanding of stellar physics, gamma-ray bursts act as lighthouses across the vast expanse of space. They illuminate the processes that govern the birth and death of stars, acting as a bridge between what we know and the mysteries that still lie beyond our reach. Antimatter, the counterpart to the matter that makes up our world, presents one of the greatest scientific mysteries. While ordinary matter is composed of protons, neutrons, and electrons, antimatter is made up of antiparticles, counterparts to these particles that carry the opposite charge. For instance, the antiparticle of the electron, known as the positron, carries a positive charge instead of the negative charge of an electron. When a particle of matter encounters its antimatter twin, the two annihilate each other in a burst of energy. This property makes antimatter a potential source of vast energy, but harnessing it for practical use has proven elusive. One of the greatest challenges in the study of antimatter is its scarcity. According to the leading theories of the Big Bang, equal amounts of matter and antimatter should have been created in the early universe. However, the antimatter that should have existed seems to have vanished, leaving behind a universe dominated by matter. This imbalance between matter and antimatter remains one of the most profound puzzles in modern physics. The search for antimatter not only challenges our understanding of the universe's origins, but also opens the door to potential breakthroughs in energy production and even space exploration. Yet, the more we study antimatter, the more we realize just how much there still is to uncover about the very fabric of the universe itself. However, our observable universe is predominantly composed of matter, with only trace amounts of antimatter detected. This imbalance presents a profound mystery that has puzzled scientists for decades. Where has all the antimatter gone? Several researchers suggest that small differences in the behavior of matter and antimatter could have played a significant role in this disappearance. These subtle deviations might point to unknown aspects of physics that challenge and expand our current understanding of the cosmos. Antimatter itself is not only a puzzle, but also a potential powerhouse of untapped possibilities. Imagine harnessing its energy. Scientists have proposed using antimatter for groundbreaking technologies, ranging from advanced propulsion systems for space travel to revolutionizing medical imaging. Positron emission tomography, PET scans, for example, rely on tiny quantities of antimatter to generate highly detailed images of the human body's internal processes. This technique is already an invaluable tool in modern medicine, offering crucial insights into the functioning of organs and tissues. Yet, the production of antimatter remains an expensive and energy-draining endeavor, limiting its practical applications for now. Still, the potential is undeniable, and researchers are tirelessly exploring ways to unlock its full capabilities. Furthermore, the study of antimatter goes far beyond practical applications. It is a key to understanding the very formation and structure of the universe. The questions surrounding antimatter, such as whether it's possible to produce or detect more of it, or what would happen if antimatter-rich regions were found in the cosmos, could reveal deeper truths about the laws of nature. As we explore the universe's vast expanse and attempt to unravel the mysteries of reality itself, antimatter stands as an enticing frontier, inviting us to explore the fundamental truths of existence. In a different part of the cosmic spectrum, we encounter magnetars, a unique class of neutron stars with extraordinarily powerful magnetic fields. Like all neutron stars, magnetars are born from the remnants of supernova explosions. However, magnetars are the extreme form of this stellar remnant. While a typical neutron star's magnetic field is already immense, about 1 million times stronger than Earth's, magnetars boast fields that can reach a staggering 1,000 times that strength, reaching up to 1 quadrillion Gauss. This immense magnetic force leads to a host of exceptional properties and behaviors that captivate scientists. One of the most intriguing features of magnetars is their ability to release bursts of energy that are, at times, even more intense than those emitted by the sun over the course of several years. These bursts, which occur in a matter of seconds, release high-energy gamma rays and X-rays, making magnetars some of the brightest objects in the universe. This powerful radiation allows astronomers to observe and study these cosmic giants from vast distances, providing valuable data about their inner workings and the laws of physics that govern them. Magnetars also exhibit a phenomenon known as starquakes. Just as Earth experiences seismic activity, the intense magnetic stress within the crust of a magnetar can cause sudden shifts, releasing massive amounts of energy. These starquakes not only create violent bursts of radiation, but also lead to subtle fluctuations in brightness, complicating their observation and study. As scientists attempt to understand the true nature of magnetars, these mysterious cosmic events continue to challenge our understanding of the universe, while furthering our exploration of the more exotic inhabitants of the cosmos. The Fermi paradox presents another tantalizing mystery that continues to baffle astronomers and physicists alike. Named after the physicist Enrico Fermi, the paradox poses a simple yet profound question. With billions of stars and even more planets in our galaxy, where are all the extraterrestrial civilizations? Given the vastness of the universe and the likelihood that there are countless habitable worlds, the paradox highlights the stark contrast between the high probability of alien life and the conspicuous absence of evidence to support its existence. Over the years, several theories have been proposed to explain this mystery. One such theory is the rare Earth hypothesis, which suggests that while simple life may be widespread throughout the universe, the specific conditions required to foster complex, intelligent civilizations are exceedingly rare. Factors such as a stable planet, the right atmosphere, and protective features like a large moon or a nearby gas giant could make the emergence of intelligent life much less likely. This would mean that Earth, with its perfect blend of conditions, could be an anomaly in the vastness of space. Another intriguing theory is the Great Filter, which posits that there is a significant stage in the evolution of life that is extraordinarily unlikely to be surpassed. This filter could exist either before or after the development of intelligent civilizations. If the filter lies before the rise of intelligence, it could mean that most species never evolve beyond simple organisms. On the other hand, if the filter occurs after the rise of intelligence, it suggests that civilizations frequently self-destruct through war, environmental catastrophe, or technological failure before they have the chance to communicate with or discover other intelligent beings in the universe. These theories, while speculative, continue to fuel the search for answers to one of the most profound questions in science. As we scan the skies, seeking signals or signs of extraterrestrial life, the Fermi paradox serves as a constant reminder of the vast unknowns that still exist beyond our understanding, and of the many challenges that lie ahead in our quest to unlock the secrets of the cosmos. Some researchers have suggested a provocative idea, one that has sparked intrigue and debate: the zoo hypothesis. This hypothesis proposes that advanced extraterrestrial civilizations are aware of humanity's existence, but, like zookeepers observing animals in their enclosures, they choose not to interact with us. The analogy here is striking. Just as zookeepers observe their animals from a distance, allowing them to develop naturally without interference, perhaps extraterrestrial civilizations are doing the same with us. This hypothesis raises profound questions about the nature of intelligence, ethics, and the potential dilemmas that come with first contact. It challenges us to think about whether these civilizations have already decided, for ethical or other reasons, that humanity's development should proceed without external influence. As we grapple with the Fermi paradox, which questions why we have yet to detect signs of intelligent life beyond our planet, the zoo hypothesis becomes not only a scientific puzzle, but also an invitation to ponder our role and place in the vast, mysterious cosmos. Equally captivating is the phenomenon of cosmic rays, high-energy particles from outer space that constantly bombard Earth. These particles, which include protons, electrons, and atomic nuclei, often travel at nearly the speed of light. When scientists detect cosmic rays, they're able to unlock valuable information about the universe and the cataclysmic processes that generate these powerful phenomena. By analyzing the composition and energy of cosmic rays, researchers can trace their origins, deepening our understanding of the environments that propel these particles to such extreme velocities. One of the most intriguing discoveries is the connection between cosmic rays and some of the universe's most violent and dynamic events: supernovas, black holes, and neutron stars. These cosmic behemoths act as accelerators, propelling particles to unimaginable speeds. As cosmic rays traverse the Earth's atmosphere, they collide with molecules in the air, producing secondary particles in the process. By detecting these secondary particles with ground-based observatories, scientists can trace the path of the cosmic rays back to their sources, offering us glimpses into the immense forces at work far beyond our world. Moreover, the study of cosmic rays offers insights into the very building blocks of the universe. When these rays interact with other particles, they sometimes generate new types of matter, particles that could hint at phenomena beyond the current understanding of particle physics. Some high-energy cosmic rays appear to be connected to far-off astrophysical events, establishing a fascinating link between our planet and the farthest reaches of the universe. But cosmic rays do more than just inform us about the cosmos. They also influence our own planet. The interactions of these rays with the Earth's atmosphere can produce clouds, which in turn can affect weather patterns. As scientists study these interactions, they are piecing together how cosmic forces might be influencing life on Earth. The exploration of cosmic rays enriches not only our understanding of high-energy particles, but also reveals the surprising interconnectedness between cosmic events and terrestrial conditions, showcasing how deeply embedded we are in the larger universe. Another enigma that continues to puzzle scientists is dark matter, a mysterious substance that accounts for approximately 27% of the total mass and energy in the universe. Though invisible, dark matter's presence is inferred from its gravitational effects on visible matter. For instance, galaxies rotate at speeds that should cause them to break apart, yet they remain intact, suggesting an unseen mass exerting gravitational pull. However, dark matter exhibits some peculiar behaviors that defy our current understanding of the universe's structure. One of the most intriguing aspects of dark matter is its tendency to cluster. Observations show that dark matter forms dense halos around galaxies, but these halos often don't match the distribution of visible matter, adding complexity to our models of how galaxies and clusters interact on a cosmic scale. Additionally, there is the mystery of dark matter's interactions. While it's believed that dark matter interacts primarily through gravity, some theories suggest that it may also engage in weak interactions, though these have yet to be confirmed. Experiments designed to detect such interactions have produced inconclusive results, leaving scientists in a state of uncertainty. If dark matter does indeed have interactions beyond gravity, it could radically alter our understanding of the fundamental forces governing the universe, potentially reshaping everything from particle physics to cosmology. These enigmatic behaviors highlight just how much we still have to learn about the universe. And as researchers continue to refine their theories and gather new data, the quest to unveil the nature of dark matter promises to push the boundaries of our knowledge even further. Every new discovery brings us closer to understanding dark matter, but with each revelation, more questions arise, keeping the field of cosmology dynamic and full of wonder. In 2009, the launch of the Kepler space mission marked a milestone in the search for planets beyond our solar system. Its primary goal was to identify exoplanets, planets that orbit stars outside our solar system, and in particular, those located in the habitable zone. This zone refers to the region around a star where conditions might allow for liquid water to exist, an essential ingredient for life as we know it. The mission captured the public's imagination, sparking curiosity about the potential for life on planets beyond Earth. Kepler's main tool for discovering exoplanets was a sophisticated telescope equipped with a highly sensitive photometer. This instrument measured the brightness of stars with extraordinary precision, detecting the slight dimming that occurs when a planet passes in front of its host star. This method, known as the transit method, allowed Kepler to spot planets even smaller than Earth. The mission's success was remarkable. It discovered thousands of exoplanets, many of which were in the habitable zone, suggesting that Earth-like planets could be common throughout the galaxy. Beyond counting planets, Kepler revolutionized our understanding of planetary systems. It revealed that many stars host multiple planets of varying sizes, from gas giants larger than Jupiter to rocky planets similar to Earth. This wealth of data has given astronomers a better understanding of how planetary systems form and evolve. It has also helped categorize exoplanets based on their size, orbital characteristics, and their potential to support life. Kepler's discoveries laid the foundation for future explorations of exoplanets, stimulating interest in studying their atmospheres, compositions, and habitability. As we continue to learn more about these distant worlds, the question of extraterrestrial life remains at the forefront of scientific inquiry. Kepler's findings have ignited an ongoing dialogue about life beyond Earth, reminding us how much we still have to discover about our place in the universe. On Mars, the exploration of the planet's surface through rovers and landers has yielded some extraordinary findings. Since the first successful landing of a rover, the scientific community has focused on uncovering Mars's mysteries. Each new mission has provided valuable data about the planet's geology, climate, and its potential for past life. One of the most significant discoveries has been evidence of water in various forms. Analysis of soil and rock samples has confirmed that liquid water once flowed on the planet's surface, and ice is present at both poles and beneath the surface. This finding is a pivotal piece of the puzzle in understanding Mars' history. Rovers like Spirit, Opportunity, Curiosity, and Perseverance have provided critical insights into Mars' volcanic activity and ancient environment. For instance, Curiosity discovered sedimentary rocks that suggest Mars may have once had conditions suitable for life, resembling some of Earth's most hospitable environments. These findings paint a picture of a time when Mars had a more Earth-like climate, complete with flowing water and a thicker atmosphere. The possibility that Mars once harbored life, even if only in microbial form, continues to captivate researchers and inspires future missions aimed at unraveling the planet's past. Through these efforts, we are not only learning about Mars, but also about the potential for life beyond Earth, opening new frontiers in our quest to understand the universe. The exploration of Martian soil has unveiled the presence of essential elements that are fundamental to life: carbon, nitrogen, and phosphorus. These elements offer scientists a glimpse into the potential for past microbial life on the red planet. Through rigorous analysis, researchers are piecing together clues that could tell us more about the possibility of life beyond Earth. NASA's Perseverance rover, the latest addition to Mars exploration, is specifically designed to search for signs of ancient life. Equipped with advanced tools, Perseverance is collecting rock and soil samples that may one day be returned to Earth for further examination. This mission also focuses on rocks that are known to preserve biosignatures, molecular traces that could hint at the presence of living organisms in Mars's distant past. These biosignatures are incredibly important because they may be the key to understanding the biological history of the planet. However, the mission does not solely concentrate on Mars's history. It is also deeply concerned with its future. Ongoing studies of Martian dust and the planet's atmosphere are helping scientists anticipate the challenges that future human explorers may face as they prepare for a potential manned mission. The knowledge gained from Perseverance and other robotic explorers is vital not just for understanding Mars's past, but also for shaping humanity's approach to colonization in the solar system. As we continue to study Mars, the mysteries of life on other planets and the potential for human colonization become more compelling and more urgent. Each discovery, each new finding on Mars sparks a cascade of questions about our place in the universe and our future beyond Earth. Could we one day live on Mars? And if so, what do we need to understand now to make that dream a reality? In 2015, another landmark mission in our understanding of the outer solar system occurred, the New Horizons spacecraft's flyby of Pluto. Before the mission, Pluto was often depicted as a desolate, icy body on the edge of our solar system. But the wealth of data sent back by New Horizons completely transformed this perception, revealing a vibrant and complex world far more intriguing than we had ever imagined. As New Horizons approached Pluto, the spacecraft provided unprecedented close-up photographs and measurements, offering scientists their first real look at the dwarf planet. The images showed a dynamic surface featuring towering ice mountains and vast, smooth plains, indicating an active geological history. One of the most striking features was a heart-shaped region, informally known as Sputnik Planitia. This area, composed primarily of nitrogen ice, is believed to be part of a vast glacial system, hinting at processes still taking place on Pluto today. Scientists were shocked to discover that Pluto's landscape includes mountain ranges with ice peaks that rival the size of the Rockies, despite its small size and great distance from the Sun. Furthermore, New Horizons revealed that Pluto has a thin but significant atmosphere, primarily made of nitrogen with traces of methane and carbon monoxide. This atmosphere changes in density as Pluto moves along its highly elliptical orbit, expanding as the planet nears the Sun and contracting as it moves farther away. These atmospheric dynamics are just one more example of the surprising complexity of Pluto, which, until recently, was thought to be an inert world frozen in time. The findings from New Horizons challenge our assumptions about distant, cold bodies in the solar system and show that they too can have rich, active environments. The data from New Horizons not only changed our understanding of Pluto, but also reignited interest in other objects within the Kuiper Belt. This mission serves as a powerful reminder that even the most distant, isolated corners of our solar system can hold fascinating secrets that challenge our understanding of planetary science. New Horizons has reaffirmed that our quest to understand the universe is just beginning, and the cosmos is full of mysteries waiting to be uncovered. The Cassini mission, which orbited Saturn for more than 13 years, also revolutionized our knowledge of the gas giant and its moons. One of the mission's most remarkable discoveries was made on Enceladus, one of Saturn's moons. Enceladus was initially thought to be a small, frozen world, but Cassini uncovered that beneath its icy crust lies a vast subsurface ocean. This ocean, in contact with the moon's rocky core, could potentially harbor conditions suitable for life. Cassini's most groundbreaking finding came when it flew through the plumes of water vapor and ice particles that erupted from Enceladus's south pole. By collecting samples of these plumes, the spacecraft identified organic molecules and simple sugars, essential ingredients for life. These findings have sparked new discussions among scientists about the possibility of microbial ecosystems existing in the ocean beneath Enceladus's frozen surface. Equally fascinating was the discovery of hydrothermal activity at the ocean's floor. Cassini's data suggested that warm water is interacting with the rocky bottom of the moon, much like hydrothermal vents on Earth's ocean floor that teem with life. These findings have raised the possibility that Enceladus could harbor microbial life in its subsurface ocean, making it one of the most promising candidates in the search for extraterrestrial life within our solar system. The revelations from Enceladus have expanded our ideas of habitability, offering new avenues for exploration. The Cassini mission didn't just deepen our understanding of Saturn and its moons, it also redefined our approach to studying other celestial bodies. Enceladus, with its active geology, abundant water, and tantalizing signs of potential habitability, is now a key focus in the ongoing search for life beyond Earth. Cassini has opened new possibilities for what might exist in the far reaches of our solar system and beyond. Then, in late 2021, humanity's reach into the cosmos took another giant leap with the launch of the James Webb Space Telescope, JWST. This state-of-the-art observatory marks a monumental advancement in our ability to peer into the distant universe. Unlike its predecessor, the Hubble Space Telescope, which primarily operates in visible and ultraviolet light, JWST specializes in infrared observations. This makes it ideal for studying distant galaxies, especially those located millions or even billions of light years away. As light travels across the expanding universe, it stretches into longer wavelengths, a phenomenon known as redshift. The JWST is specifically designed to capture this redshifted light, revealing galaxies and other cosmic phenomena that were previously beyond our detection capabilities. The telescope's primary mirror, which spans an impressive 21 feet in diameter, collects more light than any previous instrument, allowing JWST to observe fainter objects with greater clarity and precision. With this capability, JWST has been able to peer back in time to the very early stages of the universe, identifying galaxies that formed shortly after the Big Bang. By observing these distant galaxies, scientists can study the formative years of the universe and uncover critical information about the formation and evolution of galaxies. These insights are helping us answer some of the biggest questions in cosmology. How did galaxies form? What were the early conditions of the universe? What does the future hold for the cosmos? Through the combined efforts of missions like Perseverance, New Horizons, Cassini, and the groundbreaking observations of the JWST, humanity is making extraordinary strides in understanding the cosmos. Each mission builds upon the last, opening new doors and sparking new questions about the nature of life, the formation of planets, and the vast interconnected universe that we inhabit. As we push further into the unknown, our exploration of space continues to reveal the complexities of the universe, each discovery adding another layer to the ever-expanding story of our place in the cosmos. The James Webb Space Telescope, JWST, is nothing short of a marvel, pushing the boundaries of our ability to observe the cosmos. One of the telescope's standout features is its state-of-the-art cooling system, which ensures that its instruments are kept at extraordinarily low temperatures. This is crucial because it reduces the background noise produced by the telescope itself, resulting in significantly clearer and more accurate data. With this remarkable enhancement, JWST doesn't just capture images, it collects data of exceptional precision, opening up new possibilities for understanding the universe. The telescope's exquisite resolution allows it to capture breathtaking images and gather incredibly precise measurements of light emitted by distant galaxies. For astronomers, this means they are no longer limited to simply observing the position and shape of these galaxies. JWST's abilities allow them to peer deeper, investigating not only their physical characteristics, but also their internal composition and the complex processes happening within them. From the birth of stars to the dynamic interactions between galaxies, each image and spectrum it produces brings us closer to unraveling the mysteries of the cosmos. The impact of JWST extends far beyond the enhancement of observational capacity. It represents a paradigm shift in our understanding of the universe itself. With every new image and spectrum, we edge closer to comprehending the vast complexities of cosmic history. As we probe deeper into the past, from the formation of the first stars to the intricate dance of galaxies across the vast expanses of space, we are gaining insights into the very building blocks of existence. Looking forward, JWST promises to be an indispensable tool, a cornerstone for future discoveries that will help to answer the questions that lie beyond the stars. In a similar vein, the European Space Agency's Rosetta mission significantly expanded our understanding of comets, reshaping our views on these icy bodies. The mission's groundbreaking achievement was its detailed study of Comet 67P Churyumov-Gerasimenko. By deploying the Philae lander to the comet's surface, scientists were able to perform an in-depth analysis of its composition, revealing details that had never been accessible before. This exploration provided valuable information about the primordial materials that make up our solar system, offering a unique glimpse into its early stages. One of Rosetta's most intriguing discoveries was the presence of organic compounds on the comet, some of which are complex and carbon-rich. This finding raised profound questions about the potential role comets could have played in the origins of life on Earth. Could these organic compounds have been the building blocks for life? Could comets, in their ancient travels, have seeded young planets with the necessary ingredients for life to emerge? As scientists continued to study the comet's surface and materials, they found themselves considering new theories about how life might have been transported through space, long before our planet was formed. Beyond the discovery of organic compounds, Rosetta's analysis also uncovered the physical properties of the comet itself. It was found to have a low density, indicating that it is made up of a soft, porous mixture of ice, dust, and gas. This composition suggested that the comet was a remnant from the earliest days of the solar system, a time capsule preserving ancient materials from which the planets were formed. Rosetta's findings allowed researchers to view comets not just as icy wanderers, but as critical historical records that offer clues about the birth and evolution of our solar system. Moreover, as Rosetta observed the comet's behavior, it became clear that comets are far more dynamic than once thought. As the comet approached the sun, scientists witnessed dramatic changes in its activity, including jets of gas and dust erupting from its surface. These phenomena highlighted the intense influence of solar radiation on comets, transforming them as they travel through the inner solar system. This process further reinforced the idea that comets are not just frozen relics from the past, but active participants in the ongoing evolution of the solar system. These findings from Rosetta have transformed our understanding of the delicate interplay between cosmic forces and the origins of life, emphasizing that comets are much more than just frozen remnants of the early solar system. They are vital, active time capsules that help us trace the origins of our cosmic neighborhood. Wormholes, on the other hand, represent one of the most mind-bending concepts in theoretical physics. These theoretical constructs are often described as shortcuts or tunnels that connect two separate points in space-time, allowing for instant travel between them. To visualize this, imagine space and time as a two-dimensional sheet of paper. If you were to fold that paper so that 2 points touch, a wormhole would be the tunnel passing through the fold, allowing you to jump from one point to another in an instant, bypassing the normal spatial distance between them. The concept of wormholes arises from the equations of general relativity, suggesting that under certain conditions, shortcuts through the universe might exist. These hypothetical tunnels could connect distant regions of space and possibly even different points in time. This opens up a thrilling array of possibilities. If wormholes were real, they could allow for travel across vast cosmic distances in the blink of an eye. Imagine spacecraft zooming from Earth to the farthest reaches of our galaxy, or even to entirely different galaxies within moments. However, the implications of wormholes stretch far beyond travel. If they could allow for the traversal of time as well as space, profound philosophical questions arise. Could a person travel back in time through a wormhole? Would it be possible to change historical events, or would such actions create paradoxes leading to alternate timelines? These speculative possibilities fuel both scientific inquiry and philosophical debate, as they challenge our very understanding of time, reality, and the nature of the universe itself. Despite the tantalizing prospects, it's important to remember that wormholes remain theoretical constructs. While they emerge from the elegant equations of general relativity, no physical evidence has yet confirmed their existence. The idea of wormholes for now is limited to the realm of imagination and mathematical theory, but their potential impact on our understanding of the universe is profound, prompting us to consider how deeply interconnected and mysterious the fabric of space-time truly is. The notion of a stable wormhole remains entirely theoretical, with no experimental evidence to confirm its existence. Furthermore, constructing such a passage through space-time would likely necessitate forms of matter or energy that are beyond our current understanding. The very fabric of space-time is a core concept in modern physics, representing the underlying structure of our universe. Imagine space-time as an expansive four-dimensional canvas, 3 dimensions of space and 1 of time, interwoven in an intricate pattern. This tapestry isn't static or passive. Instead, it responds dynamically to the presence of mass and energy. When objects with mass, such as stars or planets, exist within this fabric, they cause it to bend and curve around them. This curvature is what we experience as gravity. Consider the analogy of a heavy ball placed at the center of a trampoline. The ball causes the fabric of the trampoline to warp, creating a slope. If you then roll a smaller ball nearby, it will spiral inward toward the larger mass due to the curvature of the surface. In a similar fashion, smaller objects in space, such as planets, moons, or even light, follow paths that are determined by the curvature of space-time, influenced by the presence of larger, more massive bodies. This interaction dictates the motion of celestial bodies and is responsible for the orbits of planets, the behavior of light, and even the trajectory of gravitational waves. Albert Einstein's groundbreaking work on the theory of general relativity redefined our understanding of gravity. He proposed that gravity isn't a traditional force exerted by one object on another, but rather a result of the geometry of space-time itself. The more massive an object, the greater the distortion it creates in space-time. For instance, Earth's gravity pulls everything toward its center, keeping us grounded, while also holding the moon in orbit, all due to the way Earth's mass shapes the surrounding space-time. This understanding of gravity has profound implications for our broader exploration of the cosmos. It allows us to understand the motion of galaxies, the behavior of falling objects, and even predicts the existence of gravitational waves, ripples in space-time produced by catastrophic cosmic events like the collision of black holes. Space-time is not a mere theoretical abstraction, but a dynamic, tangible component of the universe itself. It is intricately woven into the fabric of cosmic phenomena, influencing everything from the movement of planets to the bending of light across vast distances. Einstein's revolutionary theories, special and general relativity, transformed the way we perceive space and time. Prior to Einstein, these two entities were considered separate, absolute, and unchanging. However, Einstein's insight revealed that space and time are deeply interconnected, forming a single, unified continuum known as space-time. This new understanding implied that the universe's fabric isn't simply a stage upon which events occur. It is an active, responsive entity that can bend and warp in response to the presence of mass and energy. One of the most captivating revelations from this new perspective is the behavior of light. Rather than traveling through an unaltered, static backdrop, light from distant stars and galaxies follows curved paths due to the warping of space-time caused by massive celestial objects like stars and black holes. This phenomenon, known as gravitational lensing, allows astronomers to observe far-off galaxies and even detect unseen structures in the universe, revealing forces and phenomena previously beyond our reach. Einstein also demonstrated that time itself is not uniform. The presence of mass can slow the passage of time, creating significant differences in how time flows depending on one's proximity to a massive object. Near a supermassive black hole, for example, time slows down dramatically compared to an observer far away. While a spaceship near such a black hole might experience time moving normally, someone situated far away would perceive time passing much faster. This concept of time dilation has profound implications, not just for theoretical physics, but for practical technologies, such as GPS satellites, where adjustments must be made to account for time differences between Earth and orbit. The relationship between space and time, as illustrated by these theories, transforms our perspective on the universe. Instead of viewing it as a fixed, unchanging panorama, we now see a reality where distances stretch and time flows unevenly. Events occur not in a linear sequence, but within a complex and dynamic structure that blends space, time, mass, and energy. As our understanding of space-time deepens, we begin to explore even more mind-bending concepts, such as time loops and closed time-like curves. These ideas challenge our conventional notions of causality, suggesting that events could potentially influence themselves, creating a cyclical loop of cause and effect. In the traditional view of time, we think of it as a straight line, where one event clearly follows another. However, these new concepts suggest that time might not be so straightforward, leading to fascinating, albeit perplexing, possibilities for the nature of the universe and the way we perceive time itself. Ultimately, the study of space-time opens up a vast array of questions that challenge our deepest assumptions about the nature of reality. It forces us to reconsider how we think about space, time, and gravity, offering us a glimpse into a universe far more complex and dynamic than we could have ever imagined. Theories about wormholes, time travel, and the warping of space-time may be far from proven, but they offer tantalizing possibilities that continue to captivate the imagination of scientists and thinkers around the world. Imagine a world where the very fabric of time bends back upon itself, creating closed loops that challenge everything we know about reality. This concept, derived from Einstein's equations of general relativity, suggests the existence of closed time-like curves, a framework that opens the door to profound paradoxes and mysteries. One such paradox, known as the grandfather paradox, explores the possibility of time travel, specifically the scenario in which a person travels back to their past and interacts with their younger self. This interaction, though intriguing, raises deep philosophical and scientific questions. If the traveler alters their past by making a different choice, how can that change already be part of the timeline they're revisiting? It's a loop of cause and effect where events seem to contradict themselves, creating an enigma that challenges our fundamental understanding of time. In a universe governed by time loops, the sequence of cause and effect becomes entangled, making it hard to determine the origin of events. This ambiguity presents a serious challenge to our traditional understanding of causality. If every effect is supposed to have a distinct cause, then in a time-looping universe, could an event eventually become its own cause? The implications are nothing short of revolutionary, suggesting the need for a complete rethinking of the laws that govern our universe. While we typically think of time as a linear progression, the existence of time loops would require us to redefine time itself, possibly altering how we perceive every event in the cosmos. For both scientists and everyday thinkers, the exploration of closed time-like curves encourages us to break free from conventional narratives of time. It pushes us to question not only the nature of time, but also our place within it, urging us to consider how the past, present, and future are more interconnected than we might have imagined. Time, it seems, may not be the straight, predictable path we believe it to be. Instead, it might be a cyclical, intricate web where our actions ripple through the continuum in ways we don't yet fully understand. This remains one of the most captivating areas of modern physics, one that holds the promise of unveiling new truths about reality. Equally transformative in reshaping our comprehension of the universe was Albert Einstein's theory of relativity. His insights into space, time, and gravity revolutionized how we perceive the cosmos. However, as groundbreaking as relativity is, it faces significant challenges when trying to merge with quantum mechanics, another pillar of modern physics. While relativity governs the vast cosmic scales, the grand structures of stars, galaxies, and black holes, quantum mechanics operates in the infinitesimally small domain of atoms and subatomic particles. These two theories, though both undeniably successful in their respective realms, rely on fundamentally different principles, making their reconciliation one of the most elusive goals in physics. One of the primary points of contention between these two frameworks lies in their treatment of gravity. In general relativity, gravity is not a force in the traditional sense, but a curvature of space-time caused by the presence of mass. Massive objects like stars and planets bend the fabric of space-time, influencing the motion of other objects. Quantum mechanics, on the other hand, describes forces in terms of particles, such as gravitons, which are hypothetical particles that mediate the force of gravity on the quantum scale. The conceptual gulf between these two models makes it exceedingly difficult to understand how gravity operates at microscopic levels, leading to profound complications. Another area where these two theories clash is in the behavior of black holes. At the core of a black hole lies a singularity, a point where the curvature of space-time becomes infinite and where traditional laws of physics break down. It is in these extreme environments that the tensions between general relativity and quantum mechanics are most apparent. For instance, when considering the information that falls into a black hole, scientists are confronted with a paradox. The laws of quantum mechanics suggest that information cannot be destroyed, yet the nature of black holes seems to lead to an irreversible collapse, where information is lost forever. This paradox has become one of the central puzzles in theoretical physics. To address these issues, physicists are exploring a potential unifying theory, often referred to as quantum gravity. The goal is to reconcile the vast scales of general relativity with the minute world of quantum mechanics into a single coherent framework. Various theories, such as string theory and loop quantum gravity, are being investigated in this search for unity. Although a complete resolution remains out of reach, the ongoing effort to bridge these two worlds reflects the immense complexity of the universe and the realization that our current understanding may only be scratching the surface of a far deeper reality. Meanwhile, the exploration of exoplanets, planets that lie outside our solar system, has opened up a new frontier of scientific inquiry, combining cutting-edge technology with the principles of astronomy. One of the primary tools used to study exoplanets is spectroscopy, a technique that analyzes the light emitted or absorbed by celestial bodies. By studying how light interacts with a planet's atmosphere, scientists can uncover vital clues about its composition. This technique allows researchers to identify the chemical makeup of distant worlds, revealing the presence of elements like hydrogen, helium, and even water vapor. In recent years, breakthroughs in this field have been nothing short of extraordinary. One of the most significant discoveries was the detection of atmospheric water vapor on an exoplanet. In 2021, data from the Hubble Space Telescope confirmed the presence of water vapor in the atmosphere of WASP 121b, a distant exoplanet located over 850 light-years away. This discovery is particularly exciting because of the extreme conditions on WASP 121b, where temperatures can soar above 2,000 degrees Celsius. Such findings not only enhance our understanding of how atmospheres behave in extreme conditions, but also raise tantalizing questions about the potential for life beyond Earth. Could other planets harbor the conditions necessary for life? And if so, what does that mean for the future of human exploration and our understanding of the cosmos? These are just a few of the many avenues of inquiry that continue to push the boundaries of science. Whether it's the enigmatic nature of time, the search for a unified theory of physics, or the quest for life beyond Earth, we are only beginning to scratch the surface of the universe's profound mysteries. Every discovery brings us one step closer to understanding the fundamental nature of reality itself. In late 2021, a significant leap was made in our ability to study distant worlds when the James Webb Space Telescope, JWST, was launched. This cutting-edge observatory, equipped with state-of-the-art instruments, has revolutionized the way we explore the universe. It can now capture far more detailed spectra than ever before, unlocking a deeper understanding of exoplanets and their potential to host life. With its unparalleled ability to detect even the faintest and most distant signals, scientists are on the edge of a new era in space exploration. One of the most exciting areas of research involves the search for habitable planets in the so-called habitable zones of stars. These zones, often described as the Goldilocks zone, are regions where conditions might be just right for liquid water to exist, an essential ingredient for life as we know it. The discovery of rocky exoplanets in these zones has piqued the interest of researchers, as it suggests that life may not be confined to Earth. While the exploration of exoplanet atmospheres is still in its early stages, the pace of discovery has been exhilarating. Every new finding brings us a step closer to answering one of humanity's most profound questions. Are we alone in the universe? The possibilities are vast. As technology continues to advance, we push deeper into the cosmos, searching not only for distant planets, but also for signs of life on the icy moons of Jupiter and Saturn. These moons, Europa, Enceladus, and Titan, have become some of the most compelling targets in the search for extraterrestrial life. Despite the extreme conditions they present, these moons could harbor environments capable of supporting life, making them prime candidates for astrobiological research. Europa, for example, is encased in a thick layer of ice, beneath which lies a vast subsurface ocean of liquid water. This combination of water and potential geothermal energy makes Europa one of the most promising places in our solar system to find extraterrestrial life. The possibility of an active, water-rich environment beneath the icy surface is enough to fuel the imaginations of scientists and explorers alike. Enceladus, one of Saturn's moons, has shown remarkable signs of geological activity. Geysers of water vapor periodically erupt from its surface, suggesting the presence of an underground ocean. These plumes are not only exciting for what they reveal about Enceladus' internal dynamics, but they also represent a valuable opportunity for scientists. By studying these water vapor plumes, researchers can analyze direct samples, potentially identifying the building blocks of life, or even traces of microbial organisms. Titan, Saturn's largest moon, offers an entirely different but equally fascinating scenario. Unlike the water-rich moons of Jupiter, Titan is home to lakes and rivers of liquid methane and ethane. This alien chemistry raises intriguing questions about the nature of life. Could life forms exist in an environment based on methane rather than water? The discovery of life in such extreme and unfamiliar conditions would force us to rethink our understanding of biology, pushing the boundaries of what we consider possible in the search for life beyond Earth. The study of these icy moons is more than just an exploration of potential life elsewhere in the solar system. It enhances our understanding of planetary processes, climate evolution, and the history of our own solar system. Each new discovery could significantly alter our views on life's adaptability, expanding our concept of what types of environments could support life. With advancing technologies, we may soon unlock even more secrets from these frozen worlds, providing greater insights into the diverse habitats that exist across the universe. In parallel with these exciting discoveries, the idea of terraforming has emerged as a central theme in discussions about humanity's future in space. Terraforming refers to the process of modifying the environment of a planet to make it habitable for Earth-like life. This concept has gained traction in discussions about colonizing Mars, offering a tantalizing possibility, transforming a barren, inhospitable world into one that could support human life and even plant growth. At its core, terraforming involves altering a planet's atmosphere, temperature, and surface conditions. For Mars, this could mean releasing greenhouse gases to warm the planet and thicken its atmosphere, potentially allowing liquid water to flow on its surface. Several methods have been proposed to achieve this, such as deploying large mirrors in orbit to reflect sunlight or introducing genetically engineered microorganisms that could produce oxygen and help modify the planet's soil to support plant life. However, these ideas are not without their challenges, both technological and ethical. The potential implications of successful terraforming stretch far beyond the realm of space colonization. If we could create a habitable environment on another planet, it would open up an entirely new frontier for humanity. It could ease the pressures on Earth's dwindling resources, provide new opportunities for exploration, and even offer a means to preserve Earth's biodiversity by creating backups of species on other worlds. The dream of living on another planet, once relegated to the realm of science fiction, could one day become a tangible reality. As we continue to advance technologically and explore the cosmos, the possibility of creating a second home for humanity grows closer, offering both hope and challenges for the generations to come. However, the path toward successful terraforming remains clouded by uncertainty, as humanity continues to wrestle with understanding the intricate workings of ecosystems and the long-term consequences of altering entire planets. The ethical debate surrounding our ability to manipulate other worlds and the weighty responsibility that comes with it is an unavoidable consideration. While the idea of transforming a barren planet into a thriving Earth-like world is undoubtedly captivating, it forces us to question not only how we could change the planets around us, but also what our fundamental relationship with the universe should be. In recent years, missions to Venus have provided a wealth of astonishing insights, offering a closer look at the planet's geological makeup and climate dynamics. These revelations have illuminated both surprising similarities and stark differences between Venus and Earth. One of the most significant discoveries emerged from data gathered by the Akatsuki orbiter, which has been studying Venus's atmosphere since 2016. The findings revealed that while Venus and Earth are both rocky neighbors in the solar system, they are separated by a chasm of environmental differences. Venus is shrouded by an atmosphere that is both thick and toxic, creating conditions far harsher than anything we experience on Earth. The surface temperature on Venus is an extreme 300 degrees Celsius, making it the hottest planet in our solar system. This intense heat is a result of a runaway greenhouse effect, where the thick carbon dioxide-rich atmosphere traps heat in a cycle that causes temperatures to soar, far surpassing those of Mercury, which is much closer to the Sun. Earth, by contrast, enjoys a temperate climate thanks to a delicate balance in its atmosphere, supported by the presence of oceans that regulate temperature. Venus's surface is a bleak, volcanic landscape, dominated by massive plains, towering mountains, and highland regions. Radar maps from missions like Magellan, which began in the early 1990s, and more recent observations have revealed numerous volcanic features, suggesting that the planet remains geologically active. This is in stark contrast to Earth, where tectonic movements and erosion are constantly reshaping the surface. The geological history of Venus is a tale of a planet shaped by unique atmospheric conditions, where the absence of liquid water has meant that erosion has been minimal, leaving the planet's surface relatively young, around 300 million years old. The study of Venus does not merely deepen our understanding of one distant world, but also holds vital lessons for our own. As Earth faces the mounting challenge of climate change, the exploration of Venus's extreme climate offers critical perspectives on how planetary environments function under extreme conditions. By studying the dynamics of Venus's atmosphere, scientists can better understand the possible consequences of uncontrolled greenhouse effects, providing a sobering reminder of what could happen to Earth under similar circumstances. This research, combined with the ongoing study of other planetary bodies, is prompting scientists to reconsider how we categorize planets and their atmospheres. It is reshaping the way we view the broader universe, influencing theories on planetary formation and climate dynamics. For us, it's not just about discovering new planets or studying distant worlds. It's about using these explorations to refine our understanding of our own planet's future and how we might avoid similar ecological disasters. At the same time, the discovery of exoplanets, planets that orbit stars beyond our solar system, has radically shifted our understanding of how planets form and evolve. For centuries, planetary formation theories were based largely on our observations of the 8 planets orbiting the Sun. Scientists believed that planets coalesced from the gas and dust surrounding a young star, slowly accreting material over time. However, the discovery of thousands of exoplanets since the mid-1990s has revealed a stunning variety of planetary types, compositions, and orbital patterns that go far beyond what was originally expected. Among the most intriguing of these exoplanets are the so-called hot Jupiters, giant gas planets that orbit perilously close to their stars. These planets challenge traditional models of planetary migration, suggesting that planets do not necessarily remain in the same location where they formed. The discovery of such planets, along with many others that exhibit unique features, has led scientists to reconsider the forces and factors involved in planetary formation. It's now understood that various elements, ranging from the composition of the protoplanetary disk to the gravitational influences of nearby stars, play a crucial role in shaping how planets develop. This recognition has led to a shift in planetary science, with researchers now pursuing a broader, more inclusive theoretical framework that accounts for the vast diversity of planets in our galaxy. As the study of exoplanets continues to expand, so too does our understanding of planetary formation. With every new discovery, we are not just expanding our knowledge of the cosmos, but are also posing profound questions about the potential for life beyond Earth. Each exoplanetary discovery brings us one step closer to understanding the complexities of the universe and raises tantalizing possibilities about life elsewhere. This search for knowledge doesn't just stop at understanding the nature of planets. It extends deep into the mysteries of the universe's earliest moments. One of the most intriguing early universe is the phenomenon of cosmic inflation. Just moments after the Big Bang, the universe is believed to have expanded at a mind-boggling rate, faster than the speed of light. This rapid expansion begs the question, what triggered such an extraordinary event? Understanding the origins of cosmic inflation could unlock profound insights into the fundamental structure of the universe as we see it today. Another enduring mystery is how the large-scale structures of the universe, galaxies, clusters, and superclusters, came into being. While we have a solid understanding of how matter behaves under the influence of gravity, the exact process by which clumps of matter coalesced into the galaxies we observe today is still not fully understood. In the early universe, matter existed in a hot, dense state, and as it expanded and cooled, fluctuations in density likely led to the formation of the first galaxies. Yet, the specifics of how these early gravitational instabilities shaped the cosmos remain elusive and continue to captivate the minds of researchers. These are just some of the many questions that keep astronomers, cosmologists, and physicists engaged in an unrelenting quest for knowledge. While many of these mysteries are still shrouded in darkness, each discovery, no matter how small, brings us closer to unraveling the secrets of our universe. It is a journey filled with challenges, but also one of extraordinary potential, one that promises to reshape our understanding of where we came from, where we are, and where we might be heading. The universe, vast and enigmatic, constantly pushes the boundaries of human understanding. Two of its most perplexing and elusive components, dark matter and dark energy, form the basis for some of the most profound questions that challenge modern science. Together, these invisible forces constitute about 95% of the total energy density of the cosmos. Yet, their very nature remains a mystery. While dark energy is thought to drive the accelerated expansion of the universe, dark matter is believed to have played a crucial role in the formation of structures in the early universe. Its gravitational influence helped shape galaxies and clusters, laying the groundwork for the cosmic structures we observe today. But despite their undeniable presence, scientists have yet to identify what dark matter truly is, making it one of the most tantalizing enigmas in contemporary physics. Alongside these mysteries lies another, the imbalance between matter and antimatter. According to the prevailing theories of the Big Bang, the birth of the universe should have resulted in equal quantities of both. However, our universe appears to be overwhelmingly composed of matter, with antimatter being conspicuously absent. This asymmetry challenges our understanding of the fundamental forces of nature and raises questions about the universe's very origins and ultimate fate. How did this imbalance occur? This enigma could not only reshape our knowledge of particle physics, but also offer critical insights into the destiny of the cosmos itself. As we grapple with these profound questions, we turn our attention to the phenomenon of gravitational lensing, an effect that opens new windows to the universe. Gravitational lensing occurs when massive objects, like galaxies or galaxy clusters, bend the light coming from objects behind them. This phenomenon is a direct consequence of Einstein's theory of general relativity, which describes how mass and energy warp the fabric of space-time. When light from a distant star or galaxy passes near a massive object, its path is altered by the object's gravitational field. This bending of light creates a magnified, often distorted image of the distant object. In some cases, it can even produce multiple images or striking arcs and rings. This distortion isn't just an optical illusion. Scientists harness it to study the universe in ways that would otherwise be impossible. Gravitational lensing is invaluable in uncovering the properties of far-off galaxies, many of which are too faint to be detected with conventional methods. By observing how light from a distant galaxy is distorted as it passes through the gravitational field of a foreground object, astronomers can gain insights into the shape, structure, and composition of both the foreground and the background objects. This method allows researchers to determine the distance to these galaxies, explore their chemical makeup, and even discover their age. Moreover, gravitational lensing plays a pivotal role in investigating dark matter. Since dark matter does not emit, absorb, or reflect light, it is invisible to traditional telescopes. However, its presence can be inferred by the way it bends light from distant objects. By carefully mapping the distortion of light, scientists can infer the distribution of dark matter in galaxy clusters, revealing the unseen yet crucial components of the universe. In this way, gravitational lensing has revolutionized our ability to study the cosmos, offering a glimpse into the hidden forces that shape the universe. This technique has had profound implications for our understanding of the universe's large-scale structure. As astronomers peer deeper into space, they are able to trace the formation of galaxies, the evolution of star systems, and the fundamental forces that govern the cosmos. The study of gravitational lensing continues to offer new insights, pushing the boundaries of what we know about the universe and our place within it. In another fascinating corner of the universe lies the Great Attractor, a gravitational anomaly that has sparked a wave of curiosity and exploration. Located in the direction of the Centaurus and Hydra constellations, the Great Attractor is pulling a vast number of galaxies toward it, including our own Milky Way. This force challenges our understanding of how galaxies interact and move within the grand tapestry of the universe. The Great Attractor's influence is not confined to a single galaxy, but affects entire clusters of galaxies, suggesting that these cosmic structures are not isolated, but interconnected by vast networks of gravitational forces. This unseen mass, which is believed to contain billions of solar masses, is thought to be an expression of dark matter. Its gravitational pull affects galaxies on a scale never before imagined, altering their paths and shaping their evolution. The speed at which galaxies are being drawn toward the Great Attractor at remarkable velocities underscores the dynamic and interconnected nature of the universe. The discovery of the Great Attractor has also added a new layer of complexity to our understanding of dark matter. This invisible substance is thought to account for a substantial portion of the universe's mass, and its gravitational influence plays a key role in the clustering of galaxies. By studying the Great Attractor, scientists hope to unlock more clues about the distribution and behavior of dark matter. This research could not only refine our theories on galaxy formation, but also reshape our understanding of the cosmos itself, offering new perspectives on the forces that drive the universe's evolution. Through these mysteries, dark matter, dark energy, the imbalance of matter and antimatter, gravitational lensing, and the Great Attractor, we continue to probe the vast unknowns of our universe. Each of these phenomena not only deepens our appreciation for the intricacies of the cosmos, but also drives the quest for knowledge, pushing the frontiers of human understanding further into the stars. The more we learn, the more we realize how much there is still left to discover in this ever-expanding universe. The Great Attractor, an enigmatic force within the cosmos, continues to challenge our understanding of the universe's vast and intricate structure. As we map the cosmos and observe various gravitational forces at play, the mysteries deepen, revealing more about the universe's grand design. With each new discovery, we are presented with additional pieces of the puzzle of cosmic evolution. This journey not only helps us better understand how celestial structures form, but it also brings us closer to understanding our place within this ever-expanding universe. But the Great Attractor is not merely an intriguing anomaly. It represents a key that unlocks a deeper level of insight into the mechanics of the cosmos. It beckons us to look beyond our immediate surroundings and contemplate the universe's grander scale and dynamics. Through its gravitational influence, the Great Attractor guides the movement of entire galaxy clusters, offering a glimpse into the forces that govern the most fundamental aspects of cosmic structure. One of the most captivating theoretical concepts related to the universe's workings is that of cosmic strings. These one-dimensional topological defects, which could have formed in the early universe, offer intriguing possibilities for understanding how the universe evolved. Cosmic strings are theorized to be incredibly thin, yet immensely dense strands that stretch across vast expanses of space. They are not just hypothetical curiosities, but could hold the key to explaining several cosmic phenomena. Their potential to reveal the universe's earliest conditions lies in their possible origins during phase transitions in the early universe, much like how water freezes into ice when it reaches a certain temperature. According to theories of cosmic inflation, which suggest a rapid expansion of the universe immediately after the Big Bang, these cosmic strings might have formed as energy densities fluctuated during that explosive period. Cosmic strings are thought to carry profound gravitational effects, warping the very fabric of space-time itself. This could manifest as distortions in the distribution of galaxies, or even account for the peculiarities found in the cosmic microwave background radiation. Some theorists even believe that these strings may be remnants of grand unified theories that seek to unify the four fundamental forces of nature. Despite their hypothetical status, since they have not yet been observed directly, cosmic strings provide a valuable window into the relationship between gravity, space, and time. They offer tantalizing possibilities that could bridge the gap between the very large, cosmology, and the very small, quantum mechanics, challenging our understanding of both realms. As researchers continue to explore these cosmic structures, they may reveal new insights into the universe's early moments, further unraveling the mysteries of the cosmos. Studying the cosmic web, the vast network of galaxies, clusters, and voids that make up the universe's large-scale structure, presents its own set of challenges. The sheer scale of the cosmic web, stretching across more than 13 billion light-years, makes it an immensely complex subject of study. The structure is diffused, consisting of filaments that connect galaxies in a network resembling a spider's web. The vast distances involved make it difficult to observe with traditional methods, and much of the light from distant galaxies is obscured by gas and dust. This complexity requires scientists to employ advanced simulations and modeling techniques to better predict the distribution and movement of galaxies within the cosmic web. By comparing these models with observational data, researchers gain a clearer understanding of how the universe's large-scale structure came to be. One of the most significant findings has been the role of dark matter in shaping the cosmic web. Although dark matter does not emit or absorb light, its gravitational effects are profound. It has been shown to influence the distribution of galaxies, serving as an invisible scaffold that holds galaxies and clusters together. Another breakthrough came when astronomers discovered that galaxies are not randomly scattered throughout the universe, but instead follow a distinct pattern along the filaments of the cosmic web. These filaments are more than just threads of matter. They serve as highways along which gas and stars flow, dictating where galaxies form and evolve. By studying these patterns, scientists continue to uncover the intricate history of the universe, revealing not just where galaxies exist, but how they interact and evolve over time. As we deepen our understanding of the cosmic web, we gain a better appreciation of the vast and complex network that underpins the entire universe. The discovery that galaxies follow structured patterns rather than being randomly dispersed is a game changer. It offers a new lens through which we can explore the forces that shape the very fabric of the cosmos. On a smaller scale, the universe contains environments so extreme they defy our understanding of what is possible. Venus, for example, is an inhospitable world where surface temperatures soar to around 900 degrees Fahrenheit, hotter than any oven on Earth. The thick atmosphere, composed mainly of carbon dioxide and sulfuric acid, creates crushing pressure, more than 90 times that of Earth's atmosphere at sea level. Studying Venus not only teaches us about the limits of planetary environments, but also provides crucial insights into potential climate change scenarios here on Earth. Far beyond our solar system, neutron stars present another example of the extremes of the universe. These stellar remnants, born from the collapse of massive stars in supernovae, are incredibly dense. A neutron star packs more mass than our Sun into a sphere just 12 miles in diameter. The gravity on the surface of a neutron star is so intense that a sugar cube-sized chunk of neutron star material would weigh as much as the entire human population. Studying these remnants pushes the boundaries of our understanding of fundamental physics, revealing more about the forces that shape matter at the most extreme levels. Then, there is the vacuum of space itself, often considered the ultimate extreme environment. While we think of space as empty, it is far from it. The radiation intensity in space, particularly from cosmic rays, is so high that it could be deadly. Yet some microorganisms, like tardigrades, thrive in this hostile environment. Tardigrades are capable of entering a state of cryptobiosis, effectively shutting down their metabolism to survive the vacuum, extreme radiation, and temperatures of space. These resilient organisms provide valuable insight into the potential for life in the harshest environments, both within our solar system and beyond. By studying such extreme conditions, scientists continue to challenge the limits of our current scientific knowledge. These findings push us to reconsider the nature of life, the behavior of matter, and the vast range of conditions in which the universe operates. As researchers continue to probe the mysteries of cosmic strings, neutron stars, and other extreme phenomena, the boundaries of our understanding will stretch further, revealing even more about the incredible complexity of the cosmos. Life as we know it thrives in very specific conditions, but can it exist in the most extreme environments? The possibility that life might be found in the harshest, most uninhabitable corners of the cosmos is one that tantalizes scientists and researchers. One such place that offers this hope is Europa, a moon of Jupiter, which harbors vast, hidden oceans beneath its icy crust. The sheer potential for life to exist in these subsurface oceans challenges everything we understand about what makes a world habitable. Here, beneath layers of frozen ice, the possibility exists for life to not only survive, but to thrive, adapting to conditions far beyond what we thought possible. This prompts scientists to explore the very essence of life itself, pushing the boundaries of what is known about biology, resilience, and habitability. By studying these extreme environments, we gather essential knowledge about how life might adapt to survive in otherwise inhospitable places, providing critical insights into the broader possibilities of life beyond Earth. Each discovery, no matter how small, adds another piece to the puzzle of our own existence and our place in the universe. In 2017, humanity took a significant step forward in its exploration of the cosmos when the mysterious object known as Oumuamua passed through our solar system. This cigar-shaped visitor, the first known interstellar object to be detected, sparked a wave of excitement and intrigue across the scientific community. Its sudden appearance, high speed, and erratic trajectory defied typical expectations of what celestial objects from outside our solar system should look like. The object's odd shape and behavior pushed astronomers to reconsider their understanding of interstellar phenomena. Was Oumuamua a simple asteroid or comet, or did it represent something more extraordinary? Scientists quickly set to work, employing telescopic observations and computational models to study the object in greater detail. They analyzed its brightness, color, and rotation, all of which provided valuable clues about its composition. What they discovered was nothing short of astonishing. The object's characteristics suggested it didn't neatly fit into any known category of interstellar bodies. Its unexpected acceleration as it passed by the sun raised further speculation. Could it be a fragment of something much larger, possibly even a piece of technology from an advanced alien civilization? This discovery opened up new avenues of inquiry, sparking debates and investigations into other interstellar objects. The peculiarities of Oumuamua have led astronomers to develop new observational programs designed to track and classify similar objects from other star systems. The idea that objects from distant parts of the universe might not mirror anything found within our solar system has challenged long-held assumptions about the cosmos. With each new interstellar visitor that is detected and studied, scientists are forced to rethink what they know about the origins of celestial bodies. As we look out into the cosmos, it becomes increasingly clear that the universe is full of surprises. What we think we know may only be the beginning of an even greater mystery that awaits discovery. Among the invisible forces shaping the universe, magnetic fields play a subtle yet crucial role, affecting everything from the birth of stars to the evolution of entire galaxies. These fields, generated by the motion of electric charges, are present nearly everywhere, from the planets in our solar system to the vast clusters of galaxies scattered across the universe. They can be surprisingly strong in certain regions, influencing the behavior of gas and dust clouds, the very building blocks of stars. When a giant molecular cloud made up of gas and dust begins to collapse under its own gravity, magnetic fields exert both support and resistance. They help to prevent the cloud from collapsing too quickly by exerting pressure against the gravitational pull, while simultaneously guiding material toward the center of the cloud. This delicate balance between gravity and magnetism is essential for the efficient formation of stars. Without the influence of magnetic fields, the process of star formation would be drastically different, and the way stars ignite and evolve would be altered. As a star forms, its rotating mass generates and strengthens its magnetic field, which in turn influences the behavior of both material inside and outside the star. This magnetic interaction has profound implications for stellar winds, streams of charged particles that are released from a star's surface and can have significant effects on the surrounding interstellar medium. Magnetic fields, far from being passive forces, actively shape the evolution of stars and their surrounding environments. The study of these magnetic forces also enhances our understanding of the larger cosmic picture. Stars are the factories where the elements essential for life as we know it are created, and the interactions between gravity, magnetism, and the formation of these stars can provide us with invaluable insights into the origins of the very building blocks of life. As astronomers continue to explore the role of magnetic fields in the cosmos, they uncover more secrets that help to paint a clearer picture of how galaxies evolve and how the universe itself came into being. When it comes to the weather systems on gas giants, Neptune offers a particularly fascinating case. Its polar vortexes, for instance, differ in some intriguing ways from those on Earth. One of the most notable differences is their sheer size and complexity. On Earth, polar vortexes are relatively confined and influenced by the planet's land and ocean features. But on Neptune, the polar vortexes can span vast distances, sometimes stretching over thousands of kilometers. These massive, stable features allow for more intricate and sustained patterns compared to the more dynamic and variable vortexes on Earth. This difference in size and structure is a key aspect of Neptune's weather systems, providing a unique opportunity for scientists to study the behavior of atmospheric phenomena on a much larger and more stable scale. These observations help us understand the forces at play on distant planets and deepen our knowledge of the complex, ever-changing weather systems that govern planets throughout the universe. Just as magnetic fields shape the birth of stars and interstellar objects challenge our understanding of the cosmos, the study of weather systems on gas giants like Neptune offers yet another piece of the puzzle that will one day lead us to a deeper understanding of the universe and our place within it. Neptune's atmosphere presents a unique and fascinating environment, shaped by the interaction of various gases and extreme dynamics. Primarily composed of hydrogen, helium, and methane, this mixture creates distinct behaviors in the planet's winds, which can reach speeds of over 200 meters per second. The resulting turbulence from these high-velocity winds creates an atmosphere where long-lasting polar vortexes form. These vortexes can persist for months or even years, a striking feature of Neptune's atmospheric makeup. The temperature of Neptune's polar regions plays a crucial role in the stability of these vortexes. At an average temperature of -220 degrees Celsius, Neptune's polar areas are much colder than those found on Earth. This chilling environment contributes to the layered, structured nature of the vortexes, allowing them to maintain their form over extended periods. In stark contrast, the polar vortexes on Earth, although seasonal, are far more variable and susceptible to atmospheric conditions and seasonal shifts. Earth's polar vortexes often fluctuate in response to changing weather patterns, making them much more unpredictable compared to the steady, layered vortexes on Neptune. Unlike the polar vortex on Earth, whose behavior can change from season to season, the dynamics on Neptune unfold on a much larger scale. Neptune's seasons last decades due to its elongated orbit around the Sun. This prolonged cycle of seasons on Neptune means that its polar vortexes experience far more gradual changes compared to the rapid shifts of Earth's. By studying Neptune's vortexes, scientists not only gain a deeper understanding of this distant planet's complex atmospheric phenomena, but also broaden their knowledge of the atmospheric dynamics of other gas giants in our solar system and beyond. Meanwhile, in the vast expanse of space, there exists a fascinating set of gravitational zones known as Lagrange points. These are unique positions where the gravitational forces of two large celestial bodies, such as Earth and the Sun, or Earth and the Moon, create stable regions that allow smaller objects to remain in a steady orbit relative to the two larger bodies. There are 5 Lagrange points in total, labeled L1 through L5, each with its own unique characteristics and implications for orbital dynamics. L1, for instance, lies between Earth and the Sun. This point is particularly useful for solar observatories, as spacecraft positioned here can continuously observe the Sun without the interference of Earth's shadow. Just beyond Earth, L2 offers an unimpeded view of deep space, making it an ideal location for telescopes like the James Webb Space Telescope, which requires a clear and constant view of the cosmos. L3, positioned on the opposite side of the Sun, offers a somewhat isolated perspective of the solar system, hidden from Earth's direct line of sight. The remaining Lagrange points, L4 and L5, form an equilateral triangle with the two large bodies, creating stable gravitational pockets. These points are particularly valuable for missions involving artificial satellites. Objects at L4 and L5 remain in a relatively constant position relative to Earth and the Moon, or Earth and the Sun, requiring minimal energy for station keeping. This makes these points ideal for long-term scientific observations, satellite deployments, and even communication relays. The stability of these points offers opportunities to expand our exploration of space while minimizing the cost and complexity of maintaining spacecraft in orbit. The discovery and utilization of Lagrange points have enhanced humanity's ability to study space and further our understanding of gravitational dynamics. These points not only help in positioning satellites and conducting scientific research, but they also provide key strategic locations for future space missions, illustrating the elegance of celestial mechanics and the delicate balances that govern the universe. In the early 1970s, a groundbreaking discovery further advanced our understanding of the cosmos: the detection of pulsars. These highly magnetized, rotating neutron stars emit beams of radiation that sweep across space. As these beams cross the Earth, they produce regular pulses of radio waves. The first pulsar was discovered by astronomers Jocelyn Bell Burnell and Anthony Hewish, an achievement that marked a revolutionary moment in astrophysics. The discovery of pulsars not only confirmed the existence of neutron stars, but also provided an entirely new way of studying the universe. Neutron stars are the remnants of massive stars that have exploded in supernova events, and they are incredibly dense. Despite having a mass greater than that of the Sun, they are compressed into a sphere only about 15 kilometers in diameter. The regularity with which pulsars emit their pulses offers a unique opportunity for scientists to probe the extreme conditions that define these objects. By carefully studying the timing and frequency of these pulses, researchers have been able to infer critical properties of neutron stars, such as their rotation speed, magnetic field strength, and even their mass. The precision with which these pulses are emitted has also provided insights into the fundamental physics governing these dense, enigmatic remnants of stellar death, shedding light on the workings of the universe in ways previously unimaginable. In summary, the discovery of pulsars, the study of Neptune's polar vortexes, and the exploration of Lagrange points are all examples of the remarkable ways in which scientists continue to unlock the mysteries of our universe. Each of these discoveries contributes to a deeper understanding of the forces that shape our solar system, our galaxy, and beyond, allowing us to witness the complex interplay of gravitational forces, atmospheric dynamics, and the very nature of matter and energy in the cosmos. The study of pulses has led to extraordinary advancements in our understanding of gravitational physics. In particular, the detection of pulses in binary systems, where two neutron stars orbit each other, has provided an unparalleled laboratory for testing Einstein's theory of general relativity. As these neutron stars orbit, they produce gravitational waves, ripples in spacetime that Einstein predicted over a century ago, but were only directly detected much later. These observations of binary pulses have validated numerous predictions made by relativity, while also offering scientists the ability to measure how gravitational wave emissions influence the star's orbital dynamics. The impact of detecting these pulses has been transformative. It has not only deepened our comprehension of neutron star properties, but it has also reinforced the fundamental principles of physics. The intricate dance between light and gravity, as revealed by pulses, continues to captivate and inspire ongoing research. This research has become a crucial tool in unlocking the mysteries of the universe, one pulse at a time. By studying these waves, we are beginning to peer deeper into the cosmos, revealing secrets that were once beyond our grasp. Spectroscopy, too, has played a pivotal role in our quest to understand the universe. By splitting the light from stars and galaxies into its constituent colors, scientists can extract an immense amount of information about their composition. This technique allows astronomers to identify the unique fingerprints of various elements and molecules that reside in distant objects based on how they absorb or emit light at specific wavelengths. When light passes through a prism or diffraction grating, it creates a spectrum, a pattern of colors, much like a rainbow. Each element emits or absorbs light at precise wavelengths, which appear as distinct lines in the spectrum. By comparing these lines with those produced in laboratory experiments on Earth, astronomers can determine which elements are present in distant stars or galaxies. Elements such as hydrogen, helium, carbon, and many others can be identified in this way. This process has opened an entirely new window into the cosmos, allowing us to gather vital information without needing to travel to these celestial bodies. Spectroscopy has not only been instrumental in identifying elements, but it has also revealed other critical details such as the temperature, density, and even motion of these distant objects. For instance, the shifting of spectral lines, known as the Doppler effect, reveals whether a star is moving towards us or away from us. This information is key to understanding the expansion of the universe and the dynamics of galaxies. As we analyze the light from increasingly distant objects, spectroscopy provides essential evidence about the history and evolution of the cosmos. Spectroscopy has revolutionized astronomy, allowing us to map the composition of the universe and gain profound insights into its fundamental nature. Each spectrum gathered is like a treasure trove of information, a reminder of how profoundly interconnected we are with the cosmos. When astronomers look out into the vast expanses of space, they often encounter enormous regions known as cosmic voids. These vast areas contain very few galaxies and significantly less matter compared to the denser regions of the universe, where galaxies cluster together. Discovering these voids helps scientists comprehend the large-scale structure of the universe. It's like understanding the layout of a city by studying both the areas densely packed with buildings and the open spaces between them. The discovery of these cosmic voids has illuminated the intricate web-like structure of the cosmos. Galaxies don't exist in isolation, rather they are part of a vast cosmic tapestry, often referred to as the cosmic web. This web is composed of filaments of dark matter and galaxies, separated by these expansive voids. By mapping the size and location of these voids, scientists can gain crucial insights into the distribution of matter throughout the universe. This, in turn, informs our understanding of how the universe evolved over billions of years. Voids are fascinating not just because of their emptiness, but because they challenge and enrich our theories of cosmology. They act as natural laboratories, where the effects of gravity are minimal compared to denser regions. Studying these voids allows researchers to test models of how matter clumps together and how dark energy influences the universe's expansion. The existence and properties of these voids offer vital clues about the fundamental forces that shape the universe. Cosmic voids are much more than empty spaces. They are key players in understanding the architecture of the universe. Their study sheds light on the forces of gravity and dark energy and helps scientists unlock the mysteries of the cosmos, revealing how structure forms over cosmic time. Through this ongoing exploration, we are inching closer to a profound understanding of the very nature of the universe itself. The quest to study gravitational waves has experienced remarkable progress in recent years, driven by the groundbreaking observations made by the LIGO detectors in 2015. For the first time, scientists confirmed the existence of these ripples in spacetime, which are created by catastrophic events like the merging of black holes or neutron stars. This discovery not only validated predictions made by Albert Einstein a century ago, but it also opened an entirely new avenue for exploring the universe. Gravitational waves allow us to hear the cosmic symphony of celestial events, offering insights into phenomena that were previously invisible to traditional telescopes. Following LIGO's success, a network of observatories, including Virgo in Italy and later Kagra in Japan, came online. These observatories work together, enhancing the number of events we can detect and increasing the sensitivity of our measurements. Thanks to these improvements, we are now able to detect fainter signals than ever before, enabling astronomers to study more distant and intriguing events in the universe, phenomena that were previously hidden from our view. The impact of gravitational wave astronomy on astronomical studies has been profound. It is shedding light on the behavior of black holes, the formation of neutron stars, and the mechanics of supernovae. When combined with traditional electromagnetic observations, such as light from stars, gravitational wave data allows scientists to piece together a much fuller picture of the life cycles of stars and the dynamics of galaxies. This represents a paradigm shift in how we study the cosmos, focusing not just on the visible light emitted by objects, but also on the fundamental physical processes that govern the universe's most dramatic and violent events. In essence, gravitational wave astronomy is a new frontier, offering a completely different way of observing and understanding the universe. It is transforming our knowledge of the cosmos and opening up a new era in astrophysics. Gravitational wave detections are not merely scientific achievements. They stir the imagination and push the boundaries of technological progress. As researchers continue to develop more advanced and sensitive detectors, the future of gravitational wave astronomy holds the promise of even greater revelations. These breakthroughs could uncover profound secrets about dark matter, dark energy, and perhaps even offer clues about the very origins of our universe. Each discovery adds another layer to a vast and intricate tapestry of cosmic knowledge, an ongoing journey that not only deepens our understanding, but also continually ignites our curiosity about the mysteries that lie beyond our reach. Advancements in computational modeling have similarly revolutionized how we explore the cosmos. In the past, scientists depended primarily on observational data and relatively simple mathematical equations to make predictions about events like supernova explosions, the formation of galaxies, or the dynamics of black holes. Today, thanks to cutting-edge computer processing power and highly refined algorithms, researchers can create incredibly detailed models that simulate the complex interactions of astronomical phenomena. These simulations incorporate massive amounts of data, enabling scientists to model the universe's intricate workings with extraordinary precision. One remarkable application of these models is in simulating galactic collisions. Through these simulations, scientists can observe how galaxies merge and interact, tracking the evolution of these massive structures over time. These virtual experiments not only reveal how galaxies evolve, but also shed light on the distribution of dark matter, a substance that remains one of the greatest unsolved mysteries of the universe. Furthermore, computational modeling plays a crucial role in predicting and understanding celestial events like gravitational waves. By simulating the dynamics of black hole or neutron star collisions, researchers can anticipate the types of gravitational waves these cosmic events might produce, thus enhancing the capabilities of instruments like LIGO and Virgo. The insights gained from these simulations not only refine our theoretical frameworks, but also push the boundaries of our knowledge about the fundamental forces that shape the universe. As computational techniques continue to advance, the collaboration between computer science and astrophysics promises to unlock even greater discoveries. Each leap in technology brings us closer to answering some of the most profound questions about the universe's origins and the nature of phenomena that remain elusive. The vastness and mystery of the cosmos may remain, but computational modeling gives us the tools to explore its depths with unparalleled clarity and precision. Meanwhile, telescopes have also played a transformative role in shaping our understanding of the universe. Their ability to observe across the full spectrum of electromagnetic waves, ranging from radio waves to gamma rays, has opened up new realms of discovery, enabling us to see far beyond the capabilities of the human eye. Each part of the electromagnetic spectrum reveals unique insights into celestial objects, providing a more complete and nuanced picture of the cosmos. For example, while visible light can inform us about a star's color and temperature, other wavelengths expose hidden aspects of those same stars and the environments surrounding them. Radio telescopes, for instance, have uncovered vast clouds of gas and dust where new stars are being born, revealing the hidden processes of stellar formation. The ability of radio waves to peer into the darker regions of space allows astronomers to study the earliest stages of star evolution, offering glimpses of the universe's youthful phases. On the opposite end of the spectrum, gamma-ray telescopes are designed to observe the most energetic and violent events in the universe, such as supernova explosions or the high-energy environments around black holes. These extreme phenomena produce gamma rays that provide scientists with valuable insights into the physical processes occurring under conditions of immense energy. By studying these high-energy emissions, researchers can begin to unravel the fundamental laws of physics that govern these violent cosmic events. By synthesizing data from across the electromagnetic spectrum, astronomers are able to create a more complete understanding of celestial phenomena. This interdisciplinary approach, combining data from radio, infrared, visible, and gamma rays, provides a multifaceted view of the universe's complexities. It underscores how interconnected the various methods of observation are, forming a unified approach to unlocking the mysteries of the cosmos. In recent years, advancements in satellite technology have further revolutionized how scientists observe and analyze the universe. A key development in this area is the creation of more sensitive detectors and cameras, which allow astronomers to capture even the faintest light from distant celestial objects. With these advanced instruments, researchers are now able to study previously unreachable phenomena, objects and events that were once too dim to observe with older technology. By utilizing detectors across a variety of wavelengths, including visible light, ultraviolet, and infrared, scientists are able to unveil different facets of cosmic phenomena, enriching our understanding of the universe. Another groundbreaking innovation is the integration of adaptive optics into satellite systems. Originally developed for ground-based telescopes, adaptive optics can now be used in space-based observatories, compensating for the blurring effects of Earth's atmosphere. The result is far sharper, more detailed images of distant galaxies, nebulae, and other astronomical features. This enhanced clarity has opened new doors for discovery, allowing scientists to study the structures and behaviors of these distant objects with greater accuracy. The ability to see the cosmos with such precision is one of the key advancements in modern astronomy, helping to reveal the universe in ways that were once thought impossible. These ongoing innovations in satellite technology are not just enhancing our ability to observe the universe, they are reshaping our entire approach to understanding the cosmos. With each new development, scientists are better equipped to study distant galaxies, explore the dynamics of black holes, and unlock the secrets of dark matter and dark energy. In this new age of astronomical discovery, technology continues to be our most powerful tool in the quest for knowledge, pushing the boundaries of what we can observe, understand, and imagine about the universe. The advent of small satellites, particularly CubeSats, has revolutionized our approach to space exploration, unlocking a world of possibilities for both scientific research and discovery. These compact, cost-efficient satellites can be deployed in large numbers, each performing highly specific tasks such as monitoring distinct regions of space or conducting specialized experiments. Their versatility allows researchers to observe cosmic events in real time, whether it's tracking the explosive death of stars in supernovae or monitoring the motion of asteroids across the vastness of space. Imagine a swarm of miniature observatories, each gathering data from its unique vantage point, adding multiple layers of information to our understanding of the cosmos. CubeSats are not just small in size, they are powerful tools in our growing arsenal of space exploration technologies. They can send data back to Earth rapidly thanks to advanced communication systems that link them to ground stations. This swift exchange of information enables scientists to respond to cosmic events as they unfold, allowing for real-time analysis of phenomena like gamma-ray bursts and gravitational waves. Through these innovations, humanity is not simply observing the universe from afar. We are actively peeling back its many layers, uncovering the secrets of how it formed and evolved over billions of years. Each breakthrough, each piece of data sent back from these tiny satellites brings us one step closer to a profound understanding of the universe's mysteries and our place within it. Interferometers are another critical advancement in space science, amplifying our ability to detect faint and distant signals from the far reaches of the universe. These sophisticated instruments work by combining the light or radio waves captured by multiple telescopes spread over large distances into a single coherent signal. This technique significantly enhances the data we can gather from distant stars, galaxies, and other cosmic phenomena. What makes interferometers so powerful is their ability to improve resolution. This is particularly valuable when studying faraway objects. Just as two ears can help us locate the direction of a sound more accurately than one, multiple telescopes working together can pinpoint the origin of light with remarkable precision. This method allows astronomers to distinguish between objects that would otherwise appear as a single blur through a conventional telescope. Moreover, interferometers have the unique ability to filter out noise caused by Earth's atmosphere or other environmental factors. When multiple telescopes synchronize their observations and combine them into one unified image, they effectively eliminate the distortions that can otherwise obscure the signals we receive from space. This precision opens up a new window into the universe, revealing phenomena like the faint flicker of distant stars or the subtle whispers of gravitational waves. Thanks to these advancements, interferometers have dramatically expanded our understanding of the cosmos. They have enabled us to observe and study objects and events that were previously beyond our reach, leading to groundbreaking discoveries across fields like astrophysics and cosmology. With these tools, we are constantly pushing the boundaries of our knowledge, inching closer to solving the ultimate mysteries of the universe. Yet, even with all these technological advancements, astronomers still face significant challenges in their quest to understand the cosmos. One of the most pressing obstacles is the sheer scale of the universe itself. The distances involved are so vast that even light, the fastest thing in the universe, takes millions or even billions of years to travel across space. As a result, when we observe distant galaxies or the explosive deaths of stars and supernovae, we are actually seeing them as they were in the distant past, not as they are in the present moment. This time delay makes it difficult to form a complete picture of the universe's evolution and the life cycles of celestial bodies. Another significant hurdle is the faintness of distant cosmic events. As light travels through space, it loses energy and can be scattered or absorbed by cosmic dust and other particles. This dimming effect makes it incredibly difficult to detect faint signals from objects located far away. To overcome this, astronomers rely on specialized instruments such as powerful telescopes and highly sensitive detectors designed to capture the faintest signals from the deep reaches of space. This challenge drives continuous innovation in the field of astronomy, prompting the development of new technologies and more advanced observation techniques. With each new tool and each new discovery, astronomers are steadily expanding the limits of what is possible, pushing our understanding of the universe ever forward. These advances not only enhance our knowledge of the cosmos, but also bring us closer to solving some of the greatest mysteries of existence itself. The vast distances across the cosmos pose a significant challenge for astronomers, particularly when it comes to communication and collaboration. As cosmic events unfold, events that require timely analysis and sharing of data, it becomes clear how essential it is for scientists to coordinate their efforts across the globe. This task, however, is far from simple. When immediate reactions or observations are needed, the complexities multiply, and yet astronomers continually find ways to adapt. Networks of observatories and international collaborations span continents, with data, resources, and findings being shared rapidly to enhance our collective understanding of these celestial phenomena. Despite these hurdles, the universe remains an uncharted treasure trove of mysteries, eagerly awaiting discovery. Every observation made by astronomers pushes us one step closer to unlocking the fundamental processes that drive the cosmos. Technological advancements, paired with increasing global collaboration, are the twin engines propelling us forward. We are gradually peeling back the layers of the universe, not only revealing its immense scale, but also helping us to understand our place within it. A key breakthrough that has reshaped our ability to study the stars is the development of adaptive optics. Before this technology, astronomers faced severe limitations when observing the sky from Earth. The Earth's atmosphere, with its turbulent layers of air, would distort the light from distant stars and galaxies, blurring the images and making accurate observations difficult. Traditional telescopes simply couldn't overcome this atmospheric interference, leaving astronomers with unclear, fuzzy images. Adaptive optics has radically changed this by employing a sophisticated system of flexible mirrors that can adjust their shape in real time. This technology compensates for the distortions caused by atmospheric turbulence. The system can observe a nearby reference star to measure these distortions and instantly correct the incoming light. The result? Images of the cosmos that are almost as sharp as those taken by space-based telescopes. This breakthrough has had profound implications. For example, researchers can now study the intricate structure of far-off galaxies, explore the process of star formation, and even examine the atmospheres of exoplanets with far greater clarity than before. These sharp images have not only expanded our understanding of the universe, but have also sparked new questions about how it came to be and how it continues to evolve. Moreover, adaptive optics technology is continuously evolving, becoming more refined and widely implemented in observatories around the world. As each new version of the system is developed, it opens up fresh opportunities for more detailed investigations and exciting discoveries. The ability to observe the night sky with such clarity has transformed the way we view the universe, creating an entirely new realm for ground-based astronomy. With each improvement, we close the gap between terrestrial and astronomical observations, allowing for deeper exploration and discovery. Across the globe, the recognition that collaboration is essential to tackling the complexities of astrophysics is growing stronger. Institutions, researchers, and observatories are increasingly coming together, pooling their knowledge, resources, and discoveries. One prominent example of this is the United Nations International Scientific Council, which connects space agencies and research institutions worldwide. Through this cooperative framework, global missions can be organized and funding can be shared, amplifying the efforts in astrophysics and space exploration. The Event Horizon Telescope (EHT) project stands as a prime example of the power of global collaboration. This ambitious initiative united many institutions across continents with the goal of capturing the first image of a black hole. By synchronizing radio telescopes in locations as far apart as Hawaii and Europe, scientists were able to create a virtual Earth-sized telescope. This effort not only advanced technology to its limits, but also fostered new relationships among scientists from various corners of the world, all united in their mission to unravel the mysteries of black holes. Another notable partnership can be found within the European Southern Observatory, ESO, which brings together 20 countries to operate some of the most advanced telescopes in the Southern Hemisphere. By combining their expertise and resources, member nations have made groundbreaking discoveries, from identifying exoplanets to gaining new insights into dark energy. These findings have profound implications for our understanding of the universe and our role within it. Multinational collaborations have also transformed the way we observe and study gravitational waves, thanks to projects like the Laser Interferometer Gravitational Wave Observatory, LIGO. By working together across national borders, scientists have refined their ability to detect gravitational waves, ripples in spacetime caused by events like black hole mergers and neutron-star collisions. This international effort has opened a whole new way of observing the universe, revealing phenomena that were previously undetectable. Perhaps the most striking demonstration of international collaboration in recent decades is the coordinated exploration of distant planets. Space agencies around the world are no longer working in isolation. The combined efforts of NASA, the European Space Agency, ESA, and other agencies like those from India and China have transformed planetary exploration. This is not just a case of pooling resources. It's about sharing knowledge, expertise, and innovative technology. Every agency brings its unique strengths to the table, from NASA's vast experience to the European Space Agency's visionary planning, not to mention the technological advancements driven by emerging space agencies. A perfect example of this is the ongoing exploration of Mars. Each country involved has brought its own mission and objectives. NASA's Perseverance rover, for instance, is focused on searching for signs of ancient life, while the United Arab Emirates Hope Orbiter is gathering vital atmospheric data. Together, these separate missions provide a much more comprehensive picture of the Martian environment, creating a fuller understanding of the planet's potential to support life. This spirit of global collaboration is not just a trend, it is shaping the future of space exploration. With each joint venture, whether it's investigating the depths of space or the surfaces of distant planets, we are advancing toward a more complete understanding of the universe. Through teamwork, science knows no borders, and our discoveries continue to push the boundaries of what we know about the cosmos. In recent years, collaborative efforts between various space agencies and research institutions have become increasingly common as they recognize the value of pooling their resources and expertise. A shining example of this cooperative approach is the James Webb Space Telescope, which was developed through a partnership involving NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA. This ambitious project brings together the best of international collaboration, combining the knowledge, technology, and funding of multiple nations. The result is a telescope that promises to reshape our understanding of the universe in profound ways. The James Webb Space Telescope is more than just a piece of cutting-edge technology. It represents a monumental step forward in space exploration. This telescope is designed to peer deeper into the cosmos than any observatory before it, providing unprecedented views of distant galaxies, stars, and planets. But its potential goes beyond simply observing far-off worlds. Webb's observations will help scientists unlock the mysteries of the universe's origins, offering new insights into the formation of galaxies and the birth of stars. In many ways, this telescope serves as a time machine, allowing us to look back billions of years into the past, to an era when the first stars and galaxies were taking shape. However, the significance of such collaborative projects stretches far beyond the specific scientific goals they seek to achieve. These partnerships foster a sense of global unity, reminding us that the most significant challenges we face, whether in space exploration or addressing the problems of our planet, cannot be solved by any single nation alone. When we work together, we can overcome obstacles that might otherwise seem insurmountable. The collective effort required to build and operate the James Webb Space Telescope is a testament to the power of shared knowledge and international cooperation. As nations and scientific communities collaborate on such missions, they also contribute to the advancement of science on a broader scale. By combining expertise from various disciplines, researchers are able to tackle complex astronomical phenomena in ways that would not be possible within the confines of a single field of study. For instance, the blending of astrophysics with computer science has led to the development of advanced simulations that allow scientists to model cosmic events that are otherwise too vast or too distant to observe directly. This cross-pollination of ideas and techniques has been instrumental in deepening our understanding of the universe. Take, for example, the connection between astrophysics and particle physics. While these fields may seem distinct, they intersect in profound ways. Particle physics explores the fundamental building blocks of matter, while astrophysics investigates the nature of the cosmos at a much larger scale. However, research in particle physics, particularly in high-energy particle collisions, has provided valuable insights into the behavior of dark matter, a mysterious substance that makes up a significant portion of the universe's mass. By collaborating across these fields, scientists have been able to study how dark matter interacts with visible matter, contributing to our understanding of the universe's structure and evolution. Shared resources, whether they are advanced telescopes, powerful computer systems, or vast data repositories, are another key benefit of scientific collaboration. Large observatories like those used to study gravitational waves can be accessed by researchers from a variety of scientific fields. The data generated by these observatories provides a wealth of information that can be used not only to study astrophysical phenomena, but also to advance fields such as general relativity and cosmology. The gravitational wave observatories, for example, have proven invaluable in expanding our knowledge of space-time as they allow scientists to detect ripples in the fabric of the universe caused by massive cosmic events like black hole mergers. The importance of collaboration extends beyond the research community and into the public sphere as well. Educational outreach programs play a vital role in engaging people with astronomy and space science. These programs, often organized by museums, science centers, and educational institutions, help to bring the wonders of the universe closer to individuals who may not have direct access to space research. By offering hands-on experiences, such as the opportunity to view the night sky through a telescope or to hold a real meteorite, these programs make space science more tangible and accessible. Such outreach initiatives are effective in sparking curiosity and fostering a deeper understanding of the cosmos. When people are able to directly engage with the material, whether through interactive exhibits or community workshops, they form a personal connection to the universe. This connection is often the catalyst for a lifelong interest in science. Many of these programs are designed for a wide range of ages, ensuring that both children and adults can engage with the subject matter. In doing so, they help cultivate a future generation of scientists, engineers, and mathematicians who may go on to make their own contributions to the exploration of space. In addition to sparking curiosity, these outreach programs often work in partnership with local schools to create educational curricula that align with academic standards. This not only enhances the classroom experience, but also bridges the gap between formal education and real-world exploration. By integrating space science into the curriculum in meaningful ways, these programs encourage students to see the relevance of astronomy to their everyday lives, while also igniting their passion for further exploration. For many, this early exposure to space science is the first step toward careers in fields like science, technology, engineering, and mathematics, STEM. Through these diverse efforts, whether through international collaborations like the James Webb Space Telescope, interdisciplinary partnerships, or educational outreach, our understanding of the universe is being continually expanded. These efforts highlight the power of working together, combining different perspectives, resources, and areas of expertise. As we look toward the future, it is clear that the keys to unlocking the secrets of the cosmos lie not just in the hands of a few, but in the collective hands of the global community. The night sky has always captivated us, an eternal reminder of the vastness and mystery that surrounds our tiny world. Yet, it's not just a silent witness to our dreams and ambitions. It has also inspired a powerful wave of engagement through community-driven events such as star parties and public lectures. These gatherings amplify the shared sense of awe, excitement, and wonder that comes with gazing into the cosmos. When people come together to explore the heavens, they don't just look at the stars, they build connections with one another, united by a common purpose. In these moments, a deeper appreciation for our place in the universe emerges, fostering a sense of shared responsibility and enthusiasm for the future of space exploration. The role of education in this movement cannot be overstated. Educational outreach programs do more than spark curiosity. They ignite a lifelong passion for learning, creating advocates for science along the way. These programs encourage individuals to view the universe not just as something to observe, but as something to actively engage with, empowering them to take part in the scientific process and become lifelong learners themselves. In recent years, citizen science projects have become a cornerstone in expanding the frontiers of space exploration. These initiatives invite ordinary individuals to join scientists in their research efforts, contributing to a vast pool of data that would otherwise be difficult, expensive, or time-consuming to gather. One of the most notable examples is Galaxy Zoo, a project where volunteers classify galaxies based on images captured by telescopes. Since its inception, participants have helped classify millions of galaxies, transforming the project into a groundbreaking tool for accelerating our understanding of the cosmos. Each volunteer's classification is a small piece in a much larger puzzle, revealing how galaxies form and evolve over time. Citizen science projects also leverage the power of technology. Today, anyone with an internet connection can analyze real data from telescopes and spacecraft, using personal devices to engage in cutting-edge research. This interaction doesn't just benefit the scientists. It helps build a sense of community among enthusiasts from all walks of life. People from different backgrounds, professions, and nations can collaborate in real time, fostering a collective spirit of exploration. As more and more people participate, the scope of scientific research expands and science becomes more accessible, democratic, and inclusive. The benefits of citizen science go beyond simply collecting data. They help transform passive spectators into active participants in the scientific journey. As individuals contribute to projects, they gain a deeper understanding of the universe and the methods by which we learn about it. This, in turn, cultivates a broader appreciation for science as a process and deepens our connection to the cosmos. With this democratization of knowledge, the potential exists to inspire the next generation of scientists, sparking curiosity and enthusiasm for exploration that may one day lead them to the farthest reaches of space. The influence of citizen science will continue to grow as we expand our efforts to explore the universe. Looking ahead, the next generation of Mars missions is set to redefine our understanding of the red planet. These missions, propelled by the successes of previous rovers and orbiters, aim to push the boundaries of space exploration further than ever before. One of the most ambitious objectives is to return samples from Mars back to Earth, rock and soil samples that could provide critical evidence about the planet's past and potentially its ability to support life. Collaborations between space agencies like NASA and the European Space Agency, ESA, are essential to making these missions a reality. Through initiatives like NASA's Mars Sample Return Program, we're on the verge of retrieving tangible pieces of Mars for study in our laboratories. These samples will not only help us learn more about the planet's geological history, but may also provide the first concrete proof of life on Mars, past or present. Moreover, a focus on studying Mars' atmosphere is critical, as it could hold key clues about the planet's potential to support human exploration in the future. Instruments designed to analyze weather patterns and trace gases like methane will help us understand the planet's climate dynamics, information crucial for both scientific exploration and the safety of future human missions. Yet, the future of Mars exploration doesn't stop at sample collection or atmospheric study. We are already looking ahead to the technology needed to send humans to Mars, with developments underway for advanced habitats and life support systems. These technologies will pave the way for a human presence on Mars by the next decade, allowing us to live and work on the surface of the red planet, perhaps even building the foundation for future Martian colonies. But Mars is just one piece of the puzzle. As scientists continue their search for signs of life beyond our planet, other locations in our solar system have garnered significant attention. Mars is a prime candidate, with its ancient riverbeds suggesting that liquid water once flowed across its surface. However, other moons like Europa and Enceladus, orbiting Jupiter and Saturn respectively, also present fascinating possibilities. These icy moons are believed to harbor subsurface oceans, environments that could potentially support life, given the right conditions. Beyond the boundaries of our solar system, the search for exoplanets, planets orbiting distant stars, has become a vital aspect of the quest for extraterrestrial life. Using powerful telescopes, astronomers search for planets located in what's called the Goldilocks zone, where conditions might be just right for life as we know it. By studying the atmospheres of these planets for chemical signatures of life, scientists hope to uncover new worlds that could harbor life, or at least the conditions necessary for life to emerge. The search is still ongoing, and every new discovery takes us one step closer to understanding our place in the universe. The mysteries of the cosmos extend even further when we look to asteroids, ancient relics from the early solar system that may hold critical clues about its formation. Asteroids contain raw materials that could unlock answers to questions about the origins of planets, including Earth, and even life itself. By studying these cosmic travelers, scientists hope to gain insights into the building blocks of life. Additionally, asteroids are increasingly seen as a potential resource for the future. As Earth's natural resources dwindle, asteroids may provide a treasure trove of valuable materials, including rare metals and water. The latter is especially promising, as water can be split into hydrogen and oxygen, creating rocket fuel and potentially supporting human life in space. This could revolutionize space exploration, making long-term missions to Mars and beyond more feasible. This vision of asteroid mining has sparked a new frontier in technological innovation, with breakthroughs in mining techniques set to propel humanity further into the cosmos. But asteroid research is not only about resource extraction. Understanding the composition and trajectory of potentially dangerous asteroids is crucial for protecting Earth from catastrophic impacts. By studying these celestial objects, scientists can develop strategies to deflect or alter their paths, safeguarding our planet from future threats. Moreover, these missions could foster international collaboration, bringing together nations in the shared effort to protect our world while advancing our technological capabilities. As we stand on the brink of these exciting new frontiers, it's clear that space exploration is not just about reaching new worlds, it's about reimagining our place in the universe. From the farthest galaxies to the closest asteroids, each discovery invites us to look up and ask, what's out there? And with every step we take, we inch closer to unraveling the mysteries of the cosmos. The universe is vast, but it is also within our reach. Exploring the chemistry and geology of asteroids is not only about understanding these mysterious objects in our solar system, but also about unlocking potential insights into life beyond Earth. Some asteroids, composed of ancient materials, may harbor organic compounds, which are the very building blocks of life. By studying these compounds, scientists can gain a deeper understanding of the origins of life on our planet, and perhaps even the potential for life to exist elsewhere in the cosmos. This line of research doesn't just enrich our knowledge of asteroids, but also opens up a whole new realm of possibilities, influencing our broader theories on the emergence of life in the universe. In the years ahead, missions focused on asteroids promise to transform not only our scientific understanding, but also the future of human space exploration. These missions hold the potential to reshape the trajectory of our civilization, opening doors to new resources and expanding the possibilities of human presence beyond Earth. By extracting valuable minerals from asteroids, we could build the foundation for sustainable space exploration while also gaining critical insights into the fundamental processes that have shaped our solar system over billions of years. The study of lunar geology, too, offers a unique opportunity to explore the past, present, and future of our celestial neighborhood. The Moon, with its ancient, unchanging surface, is a time capsule that holds the secrets of our solar system's early history. Unlike Earth, which is constantly reshaped by natural forces like weathering, erosion, and tectonic activity, the Moon's surface has remained largely intact. This stability makes it an ideal place to study the geological events that have shaped not just the Moon, but also Earth and other planets in the solar system. By examining the Moon's craters, volcanic features, and rock formations, scientists are able to piece together the chaotic early days of the solar system. The craters themselves are key to understanding the frequency and scale of asteroid impacts, which have not only scarred the Moon's surface, but also left lasting effects on Earth and the other planets. Each crater provides valuable clues, from the size of the impactor to the age of the surface layer, allowing researchers to trace the history of cosmic collision and their impact on planetary evolution. Furthermore, lunar samples returned by Apollo missions and more recent lunar expeditions have proven invaluable in this quest for knowledge. These samples provide insights into the Moon's composition, allowing scientists to date various geological formations and infer the processes that led to their creation. For example, the discovery of ancient volcanic rocks on the Moon has shed light on its thermal history, which, in turn, helps scientists understand the geological evolution of other planets and moons, including Earth itself. As we look towards the future, lunar geology has significant implications for space exploration and resource management. The Moon's resources, such as water ice found in permanently shadowed craters, could play a crucial role in supporting human missions to the Moon and beyond. Understanding how to access and utilize these resources is essential for sustaining long-term human presence in space. The Moon, therefore, serves not only as a record of our solar system's past, but also as a stepping stone for humanity's future endeavors in space. The advances in space exploration technologies are propelling humanity towards even greater achievements. One of the most exciting innovations is in propulsion systems. Traditional rocket engines, while reliable, are constrained by their limited fuel capacity and relatively slow travel times. However, breakthroughs in electric propulsion offer the potential for faster, more efficient space travel. These new systems harness energy from sunlight or other renewable sources, enabling spacecraft to reach distant destinations, such as Mars, in a fraction of the time it would take with conventional engines. This could dramatically reduce travel time for future manned missions, making the dream of exploring Mars and beyond much more achievable. Life support technology is also evolving rapidly, as we strive to create sustainable habitats for astronauts on long-duration missions. Particularly for missions to Mars, where resources are scarce, it is essential that astronauts have access to reliable systems that can recycle air and water, ensuring a safe and habitable environment. New environmental control systems are being developed that will allow astronauts to live and work in space for extended periods without relying on frequent resupplies from Earth. This closed-loop system is critical for the success of deep space missions and the long-term sustainability of human exploration. Robotics and automation are also set to play an integral role in space exploration. Autonomous robots have the ability to perform tasks that are too dangerous or repetitive for humans. These tasks can range from performing scientific experiments to constructing habitats on distant planets. With the ability to operate in remote or hazardous environments, these robots are essential for gathering scientific data, conducting research, and even supporting human missions on the surface of other planets. In many ways, these machines will act as companions to human astronauts, extending their reach and capabilities far beyond what would be possible otherwise. As humanity sets its sights on the stars, the technologies emerging today are laying the groundwork for a new era of exploration. With innovative propulsion, life support, and robotic technologies, the dream of living and working on other planets is becoming more achievable every day. These advances not only deepen our understanding of space, but also have the potential to transform life on Earth, opening up new frontiers in science, technology, and human achievement. The future of space exploration is bright, and the journey has only just begun. Finally, a groundbreaking shift is taking place in the field of space exploration. Researchers in biotechnology and material science are now focusing on a critical innovation: how to utilize resources found on other planets to build structures and create tools necessary for long-term habitation. This approach, called in situ resource utilization, promises to revolutionize space exploration by reducing the need for massive amounts of equipment to be transported from Earth. Instead, the materials required for building everything from habitats to machinery could be sourced directly from the extraterrestrial environment, making space missions more sustainable and cost-effective. In parallel, biotechnological advancements are pushing the boundaries of what's possible in space. One of the most promising developments is the potential for growing food in space, which could address one of the most significant challenges to long-term human spaceflight: the need for a continuous, reliable food supply. This could make the dream of permanent space settlements not just a possibility, but a tangible reality. Together, these innovations are laying the foundation for the next era of human space exploration, bringing us closer than ever before to realizing the dream of venturing into the cosmos. The fascination with the stars and our place in the universe is not a modern obsession. It stretches back thousands of years. Throughout history, artifacts from ancient civilizations have provided us with profound insights into how early humans understood the cosmos. One of the most iconic examples comes from ancient Mesopotamia, where cuneiform tablets reveal detailed records of celestial observations. The Babylonians, in particular, were deeply invested in the movements of celestial bodies. They developed complex systems to track the stars and planets, noting patterns and cycles that showcased a sophisticated understanding of astronomy. This knowledge wasn't purely academic. It had practical applications, influencing everything from agricultural practices to religious rituals. In ancient Egypt, the grandeur of the pyramids offers another testament to humanity's cosmic curiosity. These monumental structures were not only engineering marvels, but also meticulously aligned with astronomical phenomena, such as the rising, and setting of specific stars. The Great Pyramid of Giza, for instance, is aligned with astonishing precision to the cardinal points. This alignment wasn't simply an aesthetic choice. It reflected a profound belief in the celestial order and its connection to the afterlife. The Egyptians saw the stars not just as distant points of light, but as guides that influenced life, death, and everything in between. In Mesoamerica, the Mayans and Aztecs also left behind a rich legacy of astronomical knowledge. The Mayan calendar, one of their most impressive achievements, was intricately crafted to track celestial cycles. It wasn't just a way to mark time. It was a comprehensive system that incorporated the movements of the sun, moon, and planets. This calendar was deeply intertwined with Mayan cosmology and influenced everything from daily life to agricultural practices. Similarly, the Aztec calendar stone, with its detailed carvings, illustrates their reverence for celestial events such as solstices and equinoxes. These civilizations, separated by vast distances and cultures, shared a common bond, an enduring connection to the stars above them. These ancient artifacts, whether they be architectural marvels or intricate calendars, speak to a fundamental human quest to understand our place in the universe. From aligning monumental structures with celestial events to creating complex systems to track time, ancient civilizations demonstrated a profound reverence for the cosmos. Their insights continue to inspire and remind us that even in the distant past, the stars were a source of awe and wonder, shaping cultures and guiding lives in ways we are still uncovering today. Fast forward to the present, and our methods of dating cosmic events have evolved in remarkable ways. In ancient times, celestial events were often dated based on their proximity to earthly occurrences. Early astronomers relied on observations of the stars and planets, using rudimentary calendars based on the cycles of the moon and sun. While this system was effective for marking time, it lacked the precision needed for deeper, more detailed studies of the universe. With the advent of telescopes in the 17th century, however, astronomy entered a new era. Telescopes allowed astronomers to observe distant celestial bodies in much greater detail, leading to more refined methods of dating cosmic events. For instance, by studying the light emitted by stars and galaxies, scientists could begin to calculate their distance from Earth. This concept led to the development of the light year, the distance light travels in 1 year, which became a key tool for dating cosmic events. Astronomers realized that the light we see from distant stars and galaxies may have taken millions or even billions of years to reach us, inherently providing a timestamp of sorts for those celestial objects. The discovery of radioactivity in the 19th century further transformed our ability to date cosmic events. By measuring the decay of radioactive isotopes, scientists could now determine the age areas like rocks and meteorites. This principle of half-lives, which calculates the time it takes for half of a radioactive substance to decay, became a powerful tool in dating not just planetary materials, but even the age of the Earth and the solar system itself. Today, researchers combine geological dating methods with sophisticated astronomical observations to calculate the ages of stars, galaxies, and even cosmic phenomena like supernova. The use of advanced technologies, such as computer simulations and data from space telescopes, has brought a level of precision to these calculations that was previously unimaginable. This evolving process of dating the cosmos not only enhances our understanding of the universe's timeline, but also reflects humanity's unrelenting curiosity and ingenuity. Every new discovery reveals a little more about the vast and complex universe in which we live, deepening our appreciation of the intricate web of time and space that surrounds us. The story of life on Earth, too, is intertwined with our understanding of the cosmos. Fossil records offer a glimpse into the planet's distant past, revealing the existence of primordial life forms that flourished billions of years ago. These ancient organisms, ranging from simple bacteria to algae, tell a story that stretches back over 3.5 billion years. These early life forms didn't just exist in isolation. They played a crucial role in shaping the Earth's environment, setting the stage for the diverse ecosystems that we recognize today. The discovery of these primordial life forms challenges our understanding of life's resilience. Many of these organisms thrived in harsh conditions, surviving extreme temperatures and the lack of oxygen. Their ability to adapt and thrive in such inhospitable environments suggests that life is far more tenacious than we once believed. This discovery has profound implications for the search for life beyond Earth. If life could arise and thrive in such extreme conditions on our planet, might it also exist on other worlds, such as Mars or the moons of Jupiter and Saturn? Scientists are now considering new possibilities for where life might exist, sparking renewed interest in the search for extraterrestrial life and broadening our understanding of what it means for a planet to support life. In the grand sweep of history, from ancient stargazers to modern space exploration, humanity's quest to understand the universe is ongoing. Each new discovery brings us closer to understanding the vast and complex cosmos we inhabit, and perhaps one day to reaching out into it. These fossil discoveries compel us to reassess the timeline of evolution in ways that were once unimaginable. The earliest life forms, we now believe, were likely prokaryotic, simple organisms that lacked a nucleus, a key feature of more complex life that evolved later. These prokaryotes were the pioneers of life on Earth, and studying their characteristics and activities opens a window into the very processes that led to the rise of more intricate organisms, such as plants, animals, and eventually humans. The fossil record provides us with a critical resource for tracing the history of Earth's climate and its long-term changes. The metabolic activities of ancient life forms played a central role in transforming the planet's atmosphere. These processes contributed significantly to the creation of essential elements like oxygen, which were vital for the evolution of more complex life. This relationship between life and the environment, which began in the earliest days of Earth's history, continues to resonate today in debates surrounding climate change and biodiversity. It serves as a reminder of the delicate and intricate balance between living organisms and the environments in which they thrive. By exploring the story of these primordial life forms, we not only deepen our understanding of life's origins, but also gain a profound appreciation for the web of connections that bind all living things. Each strand of life is part of a grand narrative unfolding across billions of years, and we are still discovering new chapters in this ongoing tale. In a similar vein, stellar archaeology is an exciting field that allows scientists to reconstruct the history of the universe. Just as traditional archaeology digs through human history by studying artifacts, stellar archaeology looks at the remnants of ancient stars. By examining the chemical signatures and movements of stars, scientists can unlock clues about the evolution of the cosmos itself. Each star is like a time capsule, carrying with it a record of the processes that shaped it. This provides invaluable insight into the characteristics of the galaxy and the universe at different points in their histories. A particularly intriguing aspect of stellar archaeology is the study of the metal content in stars. The oldest stars, known as population 2 stars, formed when the universe was still in its infancy, a time when it had low metal levels. This reflects a more primitive state of cosmic chemistry. By mapping these ancient stars and analyzing their elemental makeup, astronomers can infer the conditions that prevailed when they were born. For example, a star with little iron suggests it was born in an era before many supernovae had occurred, as these explosive events are key to distributing heavier elements throughout the galaxy. In addition to chemical analysis, studying the movement of stars across the galaxy allows researchers to trace cosmic events. Stars that travel along similar paths may have originated from the same region of space or been shaped by related events, such as galactic mergers. Understanding the dynamics of these stellar populations enables scientists to reconstruct the history of our galaxy, the Milky Way, offering new perspectives on how it has evolved over billions of years. As technology continues to advance, the tools of stellar archaeology become more powerful. Instruments like advanced telescopes and spectrometers are enabling astronomers to study the cosmos with increasing precision, revealing ever more intricate details. In the vast expanse of the universe, every star has a unique story to tell, and by piecing these stories together, we gain a richer understanding of our cosmic origins and the incredible processes that have unfolded across time and space. At the heart of our understanding of the universe's early days is the cosmic microwave background, CMB, a faint glow left over from the hot, dense state that followed the Big Bang. This ancient radiation, still present throughout the universe, offers scientists a snapshot of the cosmos just a few 100,000 years after the birth of the universe. By studying this radiation, researchers have uncovered vital information about the conditions that prevailed during the universe's formative years as it began to cool and expand. One of the most remarkable insights gleaned from the CMB is the uniformity of the universe. When we examine the temperature fluctuations in the CMB, we see tiny variations, often more than 1 part in 100,000. These minute irregularities are believed to represent the initial density fluctuations that eventually gave rise to the large-scale structures of galaxies and clusters we observe today. In this way, the CMB acts as a cosmic map, outlining how matter was distributed in the early universe and setting the stage for the formation of stars and galaxies. Furthermore, the CMB offers key insights into the age and composition of the universe. Current measurements suggest that the universe is approximately 13.8 billion years old. This discovery has been crucial in piecing together the timeline of cosmic events, from the Big Bang to the formation of the first galaxies. The CMB continues to provide an essential tool for understanding the universe's evolution, serving as a cosmic relic that bridges the gap between the distant past and the present, and offering a glimpse into the forces that shaped the cosmos as we know it today. The cosmic microwave background, CMB, is a relic of the Big Bang, offering profound insights into the birth and ongoing evolution of the universe. It's more than just an echo of a distant past. It provides compelling evidence for the existence of dark matter and dark energy, two enigmatic components that together constitute approximately 95% of the total energy content in the universe. These unseen forces are not just passive players. They actively shape the universe's expansion and its ultimate fate. Since its discovery, the CMB has revolutionized cosmology, offering a treasure trove of data that allows scientists to test a wide range of theories about how the universe functions. By analyzing the subtle fluctuations and patterns within the CMB, researchers can delve into the deepest questions of our existence, unraveling not only where we come from, but also where we may be headed. In this sense, the CMB isn't simply a remnant of the past. It serves as a key to unlocking the mysteries of the universe's origins and its ongoing evolution. Among the many revelations that the CMB has uncovered, one of the most groundbreaking is the idea of dark matter, a concept born from the observation of peculiar behaviors in the cosmos that defy conventional understanding. The most compelling evidence for dark matter comes from the study of galaxy rotation curves. When astronomers measure the speed at which stars and galaxies rotate, they find that stars located on the outer edges of these galaxies spin much faster than would be expected based on the visible mass alone. This discrepancy suggests the presence of an unseen mass, dark matter, that provides the additional gravitational pull necessary to hold galaxies together. Without this mysterious substance, galaxies would simply fly apart. The story of dark matter doesn't end with the rotation of galaxies. Another critical line of evidence comes from the study of galaxy clusters, vast collections of galaxies bound together by gravity. These clusters exhibit gravitational effects that can't be explained by the visible matter within them. Observations of distant galaxies reveal an intriguing phenomenon called gravitational lensing, where the light from these galaxies is bent as it passes through the gravitational field of a massive object. This bending indicates that there is far more mass present than can be accounted for by visible matter alone. In other words, dark matter is necessary to explain how light behaves in the presence of massive cosmic structures. Dark matter also plays a vital role in the formation of large-scale cosmic structures. Simulations of the universe's evolution demonstrate that this elusive substance is essential for the clumping of matter, leading to the formation of galaxies and galaxy-galaxy clusters over billions of years. Without dark matter, the universe as we know it wouldn't exist. Galaxies would be too dispersed, unable to form the intricate structures we observe today. The evidence supporting the existence of dark matter is found across multiple scales, from the rotation of individual galaxies to the behavior of massive clusters. Understanding dark matter is essential not just for theoretical curiosity, but for unraveling the dynamics of the universe and how its grand structures came to be. The mystery of dark matter continues to captivate scientists, astrophysicists, and cosmologists, pushing them to explore one of the most fundamental questions of modern science. What is this invisible force, and what role does it play in the cosmos? The search for dark matter is more than just an academic pursuit. It is a journey that could reshape our understanding of the universe and reality itself. Meanwhile, dark energy, the other half of the universe's mysterious 95%, plays a pivotal role in the grand scheme of cosmic evolution. While matter, which includes everything from stars to planets to galaxies, exerts a gravitational pull that draws objects together, dark energy works in the opposite direction. Making up roughly 70% of the universe, dark energy is believed to be responsible for the accelerated expansion of the cosmos, a phenomenon first discovered in the late 20th century. When astronomers noticed that galaxies were receding from each other at an unexpectedly fast rate, they realized that the universe was not just expanding, but doing so at an ever-accelerating pace. In contrast to matter, which clusters together under the influence of gravity, dark energy silently, yet effectively, pushes objects apart. Over time, this interaction has led to a delicate balance in the universe's expansion. Initially, the gravitational forces of matter dominated the universe's dynamics, but as the cosmos expanded and matter became more spread out, dark energy began to take over, driving the acceleration of expansion. This shift in the balance of forces has profound implications for the future of the universe and its structures. In the early universe, when matter was densely packed, gravitational attraction played a central role in the formation of galaxies and large-scale structures. Over billions of years, however, the influence of dark energy has grown, reshaping the universe and influencing the fate of everything within it. Today, dark energy continues to drive the universe's expansion, and scientists are racing to understand its true nature and how it will shape the cosmos in the distant future. The interplay between dark matter and dark energy is one of the greatest unsolved mysteries in modern science, and it has captivated the imaginations of researchers for decades. As our understanding of these forces deepens, we inch closer to answering some of the most profound questions about the universe. How did it begin? How will it end? And what lies beyond the boundaries of the observable cosmos? The quest to unravel these mysteries is far from over, but with each new discovery, we take one step closer to understanding the true nature of the universe and our place within it. However, as dark energy began to assert its influence more forcefully, it gradually halted the growth of structures in the universe, creating a stark contrast between the forces of matter and the stretching, ever-expanding fabric of space itself. Galaxies continue to form and evolve, but they now have to contend with an invisible force that pulls them apart. This relentless expansion of space, driven by dark energy, shapes their interaction and connectivity in ways we are only beginning to understand. Ultimately, the interplay between dark energy and matter offers us profound insights into the fate of the universe. If dark energy continues to push against the gravitational pull of matter, we may be witnessing a future in which galaxies, once tightly bound in clusters, drift further apart. These islands of stars and planets would be isolated in an ever-expanding cosmos, a scenario in which the vast emptiness between galaxies grows unthinkably vast. Understanding this delicate balance is not merely an academic pursuit. It is the key to unlocking the very nature of our universe. Scientists are drawn to its mysteries, constantly seeking to uncover the forces that govern the grand scale of cosmic evolution. The search to understand dark matter, one of the universe's greatest unsolved puzzles, has become one of the biggest challenges in modern physics. Around the world, scientists are launching a variety of innovative experiments designed to directly detect dark matter particles, hoping to shed light on this invisible yet powerful component of the cosmos. Among the most notable efforts is the SN+ experiment at Snow Lab in Canada, which is located deep underground, far from the interference of cosmic rays and other sources of background noise. The experiment uses large volumes of liquid scintillator to detect rare interactions between dark matter particles and ordinary matter, hoping to catch even the faintest trace of these elusive particles. In South Dakota, within the depths of the historic Homestake Mine, another groundbreaking experiment, Lux Zeppelin, is underway. This ambitious project utilizes advanced detection technologies to search for weakly interacting massive particles, or WIMPs, which are among the leading candidates for dark matter. A massive tank filled with liquid xenon serves as the heart of the experiment, where scientists monitor potential collisions between WIMPs and xenon nuclei. These interactions, if they occur, would create detectable signals, providing crucial evidence that might finally confirm the existence of dark matter. Across the Atlantic in Italy, the DarkSide collaboration is making significant strides at the Gran Sasso National Laboratory. Much like its counterparts, DarkSide seeks to identify WIMPs, but with a unique twist. It employs a dual-phase argon detector to enhance sensitivity. What sets DarkSide apart is its ability to purify argon to reduce interference from other particles, increasing the likelihood of detecting a dark matter signal. This meticulous approach exemplifies the ongoing global efforts to create the most controlled environments possible for these experiments, where every detail matters in the search for dark matter. Furthering this quest, the CASPER experiment, short for Cosmic Axion Spin Precession Experiment, is tackling another possible dark matter candidate, axions. These hypothetical particles, if they exist, might interact in ways that are detectable through their influence on electromagnetic fields. CASPER's aim is to measure whether axions can cause detectable changes in the spin of atomic nuclei, a phenomenon that could finally provide evidence for their existence. These experiments, ranging from WIMP detection with liquid xenon to exploring the potential of axions, showcase the breadth and diversity of strategies being employed to uncover the hidden nature of dark matter. The results of these investigations could fundamentally reshape our understanding of the universe, offering new insights into the very fabric of reality itself. While dark energy continues to remain one of the most profound and mysterious forces in the universe, scientists have developed a variety of methods to study its effects on celestial bodies. One of the most critical tools in this endeavor is the telescope, which allows astronomers to gather data from distant galaxies and cosmic phenomena. By measuring the light emitted by these objects, scientists can determine their distance from Earth, a crucial factor in understanding how dark energy has influenced the universe's expansion over time. A key technique used to study dark energy involves observing a phenomenon known as redshift. As the universe expands, the light from distant galaxies is stretched, shifting it toward the red end of the spectrum. By analyzing this redshift, astronomers can determine how fast galaxies are receding from us, providing key insights into the rate of expansion driven by dark energy. This delicate interplay between distance, speed, and light serves as a window into the mysterious workings of dark energy, allowing us to better understand its role in shaping the cosmos. Another critical method in studying dark energy is the examination of Type 1a supernovae. These stellar explosions, which occur when a white dwarf star reaches critical mass and explodes, are considered standard candles in astronomy. By studying their brightness and frequency, scientists can track the acceleration of the universe's expansion, offering direct evidence of dark energy's impact. These supernovae have provided strong evidence suggesting that dark energy constitutes about 70% of the universe, profoundly influencing its structure and evolution. In addition to observational techniques, theoretical models play a crucial role in the investigation of dark energy. Scientists develop simulations that explore how dark energy might behave under different conditions, using a combination of observational data and mathematical models to test hypotheses about its properties. This blend of theoretical predictions and empirical observations is essential for peeling back the layers of one of science's most enduring enigmas, allowing researchers to refine our understanding of how dark energy drives the universe's expansion and the motion of galaxies. As we look toward the future, two of the most tantalizing and perplexing mysteries in modern physics stand out: dark matter and dark energy. Together, these elusive phenomena make up roughly 95% of the universe, yet their true nature remains an enigma. To uncover their secrets, scientists around the world are planning and conducting cutting-edge experiments that aim to push the boundaries of our knowledge. One of the most eagerly awaited experiments is the ongoing work at the Large Hadron Collider, LHC. The LHC recreates conditions similar to those just after the Big Bang, allowing researchers to explore the properties of particles that could be responsible for dark matter. With its unparalleled ability to simulate extreme conditions, the LHC may eventually reveal the presence of weakly interacting massive particles, WIMPs, or other exotic particles that could help explain the dark matter that makes up a significant portion of the universe's mass. Despite these groundbreaking efforts, the quest to uncover the true nature of dark matter and dark energy is far from over. Every experiment, whether conducted deep underground or in the heart of a particle collider, brings us one step closer to understanding the invisible forces that govern the cosmos. What lies ahead could change everything we know about the universe, offering new revelations that could reshape our view of reality itself. The search for answers about the fundamental forces and building blocks of our universe has led scientists down a thrilling and often unpredictable path. One of the most captivating areas of exploration today is the theory of supersymmetry. This framework proposes that every particle in the standard model of particle physics has a heavier, yet undiscovered counterpart. These hypothetical particles, if they exist, could unlock the mysteries surrounding dark matter, a force that continues to elude direct observation despite its undeniable influence on the cosmos. Supersymmetry, though still theoretical, offers a potential key to understanding not only the structure of our universe, but also the enigmatic nature of dark matter. Dark matter, which makes up around 85% of the universe's mass, interacts with ordinary matter through gravity, but it does not emit, absorb, or reflect light, making it incredibly difficult to detect. To uncover its secrets, scientists are employing sophisticated experiments. many of which take place in deep underground facilities. One such experiment is the Large Underground Xenon Lux project. Here, scientists use ultra-sensitive detectors shielded from the pervasive interference of cosmic rays, a constant threat to the clarity of such investigations. By looking for rare interactions between dark matter particles and normal matter, these detectors, filled with litters of liquid xenon, provide some of the most accurate tools for direct detection of dark matter. Each signal, however faint, brings us one step closer to unraveling the true identity of dark matter, and by extension, the workings of the universe itself. Meanwhile, another cosmic mystery, dark energy, has continued to captivate researchers. Dark energy is believed to be responsible for the accelerated expansion of the universe, like a phenomenon first observed in the late 20th century. But what is dark energy? How does it work? To answer these questions, scientists are turning to groundbreaking experiments like the European Space Agency's Euclid satellite and NASA's Wide Field Infrared Survey Telescope, WFIRST. These missions aim to map the expansion of the universe in exquisite detail, examining the distribution of galaxies and how their light has shifted over time. By studying the behavior of galaxies, researchers hope to gain a clearer understanding of how dark energy has shaped the cosmos throughout its history. As these missions continue to unfold, they promise to reshape our understanding of the universe on a profound scale. The quest to understand the cosmos doesn't stop at dark matter and dark energy. Scientists are also deepening their exploration of the very nature of life itself. Astrobiology, the study of life in the universe, that is opening new frontiers as we seek to answer the age-old question, is there life beyond Earth? A significant leap forward in this quest has been the study of extremophiles, organisms that thrive in Earth's most hostile environments. From the crushing depths of the ocean's hydrothermal vents to the blistering heat of acidic hot springs and the frozen wastelands of Antarctica, extremophiles are rewriting the rules of what is considered habitable. These remarkable organisms not only survive, but often flourish under conditions once thought to be beyond the reach of life. Their existence challenges our fundamental understanding of biology and prompts scientists to broaden their search for life beyond Earth. One of the most well-known extremophiles is the tardigrade, or water bear. These microscopic creatures are capable of surviving extreme temperatures, radiation, and even the vacuum of space. By entering a state called cryptobiosis, tardigrades essentially shut down their metabolism, allowing them to survive in conditions that would be lethal to most other forms of life. This extraordinary resilience suggests that life on other planets or moons in our solar system could adapt in similarly unexpected ways, thriving in environments we once considered too inhospitable. The study of extremophiles has also led to critical insights into biochemistry. Some of these organisms derive energy not from sunlight, but from chemical processes that involve sulfur, iron, or other compounds. This discovery has profound implications for the search for extraterrestrial life. For instance, moons like Europa, one of Jupiter's satellites, and Enceladus, a moon of Saturn, may harbor subsurface oceans beneath their icy exteriors. These environments could resemble the extreme conditions where extremophiles on Earth thrive, opening up new possibilities for finding life in places we once thought uninhabitable. As we continue to study these resilient creatures, we expand our search for life to include a broader range of environments and biochemistries than ever before. Artificial intelligence, AI, is also playing an increasingly crucial role in the search for extraterrestrial life. As researchers sift through vast amounts of data from astronomical surveys and experiments, AI provides a powerful tool for uncovering hidden patterns and signals that might otherwise go unnoticed. For instance, AI algorithms are trained to identify potential biosignatures, gases or other markers in the atmospheres of distant planets that might suggest the presence of biological activity. By analyzing the patterns found in Earth's ecosystems, AI systems can be taught to recognize similar signs on other planets, speeding up the process of discovery and enhancing the precision of our searches. The collaboration between AI and astrobiology is particularly valuable because it allows researchers to analyze data on an unprecedented scale. Machine learning algorithms can process vast data sets more efficiently than human researchers, rapidly identifying patterns and connections that might take years to uncover using traditional methods. In this way, AI is helping to refine our search for life beyond Earth, making it more targeted and accurate. As this technology advances, it may well lead to the discovery of extraterrestrial life in the not-too-distant future, transforming our understanding of the universe and our place within it. Each of these areas of research, from dark matter and dark energy to the study of extremophiles and the application of artificial intelligence, plays a part in one of the most exciting eras of scientific discovery. We are on the brink of answering questions that have fascinated humanity for centuries. With every new experiment, every breakthrough, we inch closer to understanding not only the origins of the universe, but also the profound possibility that life exists elsewhere in the cosmos, perhaps in forms we can scarcely imagine. These questions may not just be about distant stars and galaxies, but about us, our place in the universe, and the very nature of life itself. Artificial intelligence has become an indispensable tool in the realm of astrophysics and astrobiology, revolutionizing the way scientists explore the vastness of space. One of its most groundbreaking applications is in the processing of astronomical images and spectroscopic data. For instance, AI's ability to analyze the light emitted from distant stars or planets is transforming our understanding of the cosmos. By carefully examining the spectra of light, AI helps researchers detect chemical compositions, identifying substances crucial for life. When thousands of these spectra are analyzed, AI quickly and efficiently filters through the data, pinpointing signs that could suggest the presence of life-sustaining conditions. The discovery of water or organic molecules, vital ingredients for life as we know it, becomes far more accessible through this automated analysis. This shift from manual to AI-driven analysis not only accelerates research, but also shifts the focus of scientists from data processing to deeper interpretation. The impact on the field of astrobiology is profound. AI's ability to handle large-scale surveys, such as those conducted by space missions and powerful telescopes, enhances our capacity to search for habitable worlds across the universe. With our advancing technology, the collaboration between human ingenuity and artificial intelligence is opening doors to discoveries that once seemed like science fiction. The age-old question, are we alone in the universe, is slowly inching closer to an answer, as AI helps guide humanity toward a clearer understanding of potential life beyond Earth. As we turn our gaze toward the vastness of the cosmos, our curiosity pushes us to explore potential havens for life beyond the boundaries of our solar system. In recent years, the search for extraterrestrial life has gained substantial momentum, driven by technological advancements and a more refined understanding of what constitutes a habitable planet. Exoplanets, planets located outside our solar system, are some of the most promising targets for this research. These distant worlds orbit their stars within a specific region known as the habitable zone, where conditions are just right for liquid water, a critical ingredient for life, to exist. Among these exoplanets, one name stands out: Proxima Centauri b. Proxima Centauri b orbits our closest stellar neighbor, Proxima Centauri, lying just over 4 light-years away. This proximity, combined with the planet's position in the habitable zone of its star, makes it an ideal candidate for future observation. Scientists are eager to study Proxima Centauri b's atmosphere, searching for gases that could indicate biological activity. The prospect of temperate conditions on a world so close to us is a tantalizing one, fueling further interest in the study of exoplanets. Equally exciting is the TRAPPIST-1 system, which contains 7 Earth-sized planets orbiting a cool dwarf star. 3 of these planets lie within the habitable zone, raising intriguing questions about the potential for life on each. Observations from space telescopes have already revealed fascinating details about their atmospheres, and early data says that at least one of these worlds might have the necessary conditions to support living organisms. These discoveries are only the beginning of what promises to be a revolutionary era in the search for life beyond Earth. However, the search for life is not limited to exoplanets alone. The moons of gas giants like Jupiter and Saturn have also become key targets for astrobiologists. Among them, Europa, Enceladus, and Titan stand out as prime candidates for the search for life. Europa, with its icy surface hiding a vast ocean beneath, presents an intriguing mystery. Could microbial life thrive in this subsurface ocean, sheltered from the harsh environment of space? Enceladus, with its geysers that expel plumes rich in organic compounds, offers another tantalizing clue. These plumes hint at the possibility that life may be lurking beneath the moon's frozen exterior. Titan, Saturn's largest moon, presents yet another fascinating case. Its thick atmosphere and lakes filled with liquid methane create a completely different environment than what we are accustomed to, yet one that is equally worthy of exploration. Each of these celestial bodies serves as a reminder that the universe is teeming with untapped potential. The cosmos is not only a vast expanse of empty space, but also a playground full of opportunities for discovery. The study of biosignatures, indicators of life, past or present, plays a crucial role in this ongoing quest. Biosignatures are chemicals or patterns that suggest the presence of life, often in forms that are beyond our current understanding. By studying these biosignatures, scientists can begin to piece together the puzzle of which environments may support life. Certain gases, such as oxygen and methane, are particularly significant in this search. These gases interact in ways that are typically associated with biological processes. The coexistence of oxygen and methane is especially intriguing, as oxygen is produced by plants and methane is often generated by microbial life. This synergy between the two gases points toward the possibility of an active ecosystem, one that could support complex life. By detecting similar chemical signatures in the atmospheres of exoplanets, scientists are gradually constructing a roadmap that could lead them to planets capable of sustaining life. The collaboration between artificial intelligence and astrobiology is not just helping us identify the signatures of life, but also giving us the tools to study these biosignatures on a massive scale. As we refine our techniques and expand our technological capabilities, the possibilities of what we can discover in the universe are limitless. Each new planet, moon, or distant star system adds another layer to our understanding of what might be out there, waiting to be discovered. Through the power of AI, we are inching closer to answering one of the most profound questions of all: are we truly alone in the universe? Moreover, the study of Earth's biosignatures across diverse and extreme environments offers scientists a unique opportunity to establish a baseline for life's adaptability. From the intense heat of hot springs to the freezing expanses beneath ice sheets, life on Earth has demonstrated an extraordinary ability to thrive under conditions that were once thought to be uninhabitable. These findings are not just crucial for understanding life on our own planet, but also provide critical insights into where else life might exist across the universe. When examining how life adapts to such extreme conditions, researchers begin to speculate on the potential for life beyond Earth. For instance, if life can survive in the searing heat of sulfuric springs, or in the cold, dark recesses beneath ice, it suggests that other planets with similar environments might also harbor life, perhaps in forms we have yet to fully comprehend. This realization expands our imagination and our search for life, encouraging us to look beyond the familiar and to consider possibilities we might never have envisioned. In addition to studying biological markers like gases, scientists also examine geological features and the presence of water. Water, as we know it, is vital to life, and understanding how it interacts with its surroundings helps pinpoint the most promising locations for the search for extraterrestrial life. Combining the study of biosignatures, specific chemical clues that indicate biological processes, with geological evidence, scientists can better predict which types of planets and moons might offer conditions conducive to life. This interdisciplinary approach to understanding biosignatures doesn't merely illuminate the basic requirements for life, it sparks a deeper inquiry into the mysteries of our universe. By piecing together the various components that make Earth habitable, scientists are constructing models that may guide us in our quest to find life elsewhere. The study of Earth's biosignatures, then, serves as a compass pointing toward possible worlds where life might exist. Understanding the origins of life on Earth provides a crucial foundation for exploring the possibility of life elsewhere. By delving into how life began here, how basic molecules came together to form complex living systems, we gain invaluable insights into the processes that might lead to life's emergence in other environments. With this knowledge, we can better hypothesize about where life might exist beyond Earth, be it on a distant exoplanet or a moon orbiting a gas giant. For example, if we discover that life requires specific chemical compounds or a narrow temperature range to survive, we can target similar conditions on other worlds in our search. Earth's rich history offers a treasure trove of examples of how life has flourished in varied and extreme settings. From the blistering heat of volcanic lakes to the frozen deserts of Antarctica, life on Earth has exhibited an incredible resilience and capacity for adaptation. These extreme environments have not only supported life, but have also fostered its diversity. The more we understand about Earth's adaptability, the more capable we become at identifying potential life-supporting worlds beyond our own. The exploration of extremophiles, organisms that thrive in the harshest conditions, further broadens the scope of our search for extraterrestrial life. These resilient life forms have evolved to exist in environments once deemed too inhospitable for any organism to survive. If life can flourish in sulfuric hot springs or under the thick ice of the polar regions, then it's not such a stretch to imagine that similar organisms might exist in the hidden depths of oceans, beneath the icy crusts of moons, like Europa or Enceladus, or even on exoplanets with extreme climates. Ultimately, studying the origins of life on Earth does more than simply refine our strategies for searching for extraterrestrial organisms. It invites us to reflect on the nature of life itself. Understanding how life began and how it thrives in the face of adversity leads us to consider profound existential questions. What does it mean to be alive? How fragile is the balance that sustains life, and what is our place in the cosmos? In many ways, the search for life beyond Earth is not just a quest to find alien life. It's a journey toward understanding ourselves, our origins, and our connection to the vast universe around us. In the end, as we look outward to the stars, we may be searching for reflections of life as we know it, and perhaps for a deeper understanding of life itself.